look at this morning, okay, we're going to look at how we make up a waveform. So what we can look at so far, okay, what we're going to look at is the makeup of a waveform. Most radio waves, okay, most radio waves are a sine wave, okay, most radio waves are a sine wave. And a sine wave, okay, for our radio systems, when you tune in your radio, okay, it might be 98.1 kilohertz. If you're actually using your AM radio, your medium wave radio, we actually give the wavelength in meters, okay? 909 meters, 1152 meters, etc. So how do we get a waveform? Okay, or how did the whoops. Let's go back. So if I have my graph, oh, that's rubbish. Start again. So this point here, that's 0. And that point there is 0. And the definition of a wavelength is, if I take this back like so, is when the waveform passes through the same point in the same direction. So if I take this waveform back like this, you can see this waveform is passing through 0 in that direction. It does go back through 0, but you can see it's going downwards. So here we go. That is one wavelength. You can see there it's passing through 0 or the same point in the same direction. And that is what we call one wavelength. Okay, or one complete cycle. Okay, is one wavelength. The next thing is the amplitude. Okay, the height of the waveform. And the amplitude, okay, I could actually say is the voltage or the power that that waveform has. Okay, I didn't touch that. So that's the first thing you need to remember. What is a waveform made up? It's made up of wavelength, where basically the wave completes one full cycle, and the amplitude, which is the peak, okay, of the waveform, from one peak to the top of one curve to the bottom of the other. That is a waveform, okay? Now, the other thing we've talked about is something called frequency, okay? Frequency. Now, the frequency is the number of waveforms, number of waveforms, number of cycles the waveform completes in 1 second. Okay. So the frequency is the number of complete waveforms in 1 second. So if I have actually got one waveform completes in 1 second, okay, that is the frequency. And we're going to look at that right now. And there is this formula, okay? Formula, this one here, this old Greek symbol here is called lambda. It looks like an upside down Y. C is the speed of light, 3 times 10 to the 8, and the frequency is hertz. Okay. I can rearrange this to F equals C divided by lambda. Okay. C divided by lambda. And that gives me the frequency. The speed of light doesn't change. Okay. The speed of light doesn't change. 300 times 10 to the negative 6. So, if I was asked to calculate it, I need to know two variables. I need to know the wavelength, and the speed of light is already given for me. So if I now say the wavelength, okay, is 2 megahertz, okay, 2 megahertz, that equals 2 times 10 to the 6 cycles per second. So if I was asked to calculate the frequency, is F times the speed of light, which is 300 times 10 to the negative 6, over 2 times 10 to, 10 to the 6. When we're doing indices, okay, if I've got 10 to the 6 and 10 to the 6, I'll bring this 6 up, that becomes negative, so it's basically adding the indices together, so it'll be minus 6 plus 6 gives me 0, so I can score them out. So now I'm left with 300 divided by 2 gives me 150, and the units are hertz. Okay, so make sure you can rearrange that formula. Okay, just make sure you can rearrange that formula for frequency. So F, the frequency of the waveform, is the speed of light, which is 300 times 10 to the negative 6 divided by the wavelength. Okay, and we'll get that information. Right. Let's look at the understanding of relationship between frequency and wavelength. Okay. Here's the relationship. The lower the frequency, the larger the wavelength. The higher the frequency, the shorter the wavelength. How that works? That is 1 second. Yep, as a period of time of 1 second. Okay, I have 2 waveforms, so I've got 2 cycles per second. Okay, so basically I've got 2 hertz. So a low frequency, and you can see there's a large. Okay, I've completed it. Now, if I do this, if I have a red cross or an amber cross, I've increased the frequency, and you can see the waveform, the wavelength has got shorter. So There is a direct relationship between frequency and wavelength. As frequency goes up, wavelength goes down. Okay, remember that. If frequency goes up, wavelength goes down. Okay, let's look at a complex waveform. Okay, a square wave. Okay, square wave, digital. Okay, if you last time I was out there, have you got DAB radio now in Kathmandu? Is it still AM and FM? You have DAB radio.
It's both AM, FM.
AM and FM. The next waveform, the next system is going to come out, radio wave, is going to be DAB. It's digital audio broadcasting. And it's going to be a square wave, okay? Just like you talk about the data in your computer, it's all a square wave. But when we actually look at a square wave, okay, if you were to look at a square wave in an oscilloscope, you would actually see it's made up of multiple sine waves, okay? Multiple sine waves. And the two parts of these multiple sine waves we need to understand. So in a square wave, if I have this again as, it says there, one frequency. Okay, so basically that must be, that time is 1 second. So the fundamental frequency is the waveform has the same frequency as the square wave. You can see that there, that'll be that big red waveform. That's the fundamental frequency. That doesn't change whether it's an AC or a square wave, a sine wave or a square wave. But each waveform is made up of a harmonic, okay? Harmonic. And that is a multiple of the fundamental frequency. So if I had a fundamental frequency, and let's call it 1000 hertz, okay? The first, or what we call the second harmonic, is basically that divided by 2, which will be 500. Again, the third will be divided by 2, 250. Fourth, 125. So it's just a breakdown of the number of waveforms we can complete in one cycle. Okay, so a square wave has the fundamental frequency, which is the exact same frequency of the square wave. And a harmonic is just a multiple of the square waves. Okay, as you can see there, if the fundamental frequency is 1000, the second harmonic must be half that. The third will be half it again. The fourth would be 125. And that's what happens. So basically, that's what happens with harmonics. Now we're going to look at, so that's a waveform. Now we're going to look at how we create a radio wave. Okay, how we create a radio wave. We're going to look at how a radio wave is made up. A radio wave is also known as a electromagnetic wave. Okay. electromagnetic wave. So just looking at that word, electromagnetic, I've got two words, electricity, and magnetic is magnetic. So my radio wave is actually made up of two parts. It's got an electrical wave and a waveform caused by a magnetic field. How a radio wave works, okay? How a radio wave works. I'm going to get into my screen. Here's my aerial, okay? Nice little whip aerial. And what happens, okay, what happens is it's connected to an electrical supply. And I'm going to put a current down this. I'm going to put an AC current down this aerial. Okay. So that is my electrical field. And as we all know now, an electrical field, when a current goes down a conductor, it also produces a magnetic field. Okay? And at very low frequencies, the magnetic field and the electrical field have a relationship of 90 degrees. And what will happen is I start to increase the frequency of the electric field. If I start to increase in frequency, the magnetic field, okay, takes longer to change direction than the electrical field. So the magnetic field takes longer to change the direction than the magnetic field. So what happens is, as the frequency of the AC, the current on the conductor, the aerial, goes back and forward, the magnetic field changes slower. And it'll get to the point where the peak of the magnetic field doesn't collapse before this, the electrical field. And what it does is it doesn't collapse. What happens, the magnetic field blows it, the electrical field blows out that magnetic field, and that's what produces our radio wave. So you need to have a certain frequency before you can transmit, okay? And that's how we produce a radio wave. The current in the aerial pushes out that magnetic field, okay? And that's why we call it a radio wave is electromagnetic, okay? It's electromagnetic. So let's look at the relationship. First thing we need to think about is there's certain words we need to understand, okay? The direction of propagation, I could call that's my aerial or antenna, yeah? So now my electrical field, there you go, you can see it in blue. that is going up and down. So it's going back and forward down the aerial. And as it goes up and down, it produces this electromagnetic field, okay? Produces this magnetic field, because we all know current going through a conductor produces a magnetic field. So now I have my electrical field, my AC waveform going down this aerial, or what we call the direction of propagation. And the first thing we can see is it has a 90-degree relationship, okay, to the direction of propagation. But I also can say it is the magnetic field has a 90-degree angle to the direction of propagation. And as you're now looking at the two waveforms, they also have a 90-degree relationship to each other. Okay, so a radio wave is made up of two parts. The electrical field, which we call the E field. The magnetic part we call the H field, and the direction of propagation. Okay, the direction of propagation. So there's a little statement, okay, in your books, okay, and it's just above that diagram here. And as it states, the electrical field and the magnetic field are 90 degrees to each other, and both are 90 degrees to the direction of propagation. Remember that statement. Remember the relationship between the E field, the H field, and the direction of propagation. Remember that little statement. Now, the next thing you've probably heard of, okay, there we go, it said there, the E field determines polarization, H field 90 degrees, and E and H 90 degrees to the direction of propagation. The next thing we're going to look at is something called polarization. Now, you've probably heard of that before, polarization. When you look at the roofs, okay, of Kathmandu, you see all the television aerials. Yep, you see all the television. And some of the aerials, okay, they all look like this, don't they? Yeah, you've all seen those. We're not talking about the satellite television, but we're normally talking about the normal TV aerials. Have you seen aerials like this in Kathmandu? Well, I have, because I've been there. And if you notice, some of the aerials are, so basically all the little prongs, yeah, it's on its side. And then some of them are like this. Okay. So you've got one that's flat and one that's on its side. That is because the television or the radio transmitter is sending out this waveform, okay? Sending out the waveform. And the waveform is known as polarized, okay? So when you look at it now, the waveform could be what's called vertically polarized, as I'm seeing it here, it's vertically, or it could be very difficult to draw. Horizontal, so it's like a snake going across the ground. And what determines the polarization of the waveform is the E field. So remember that. What determines the polarization of a radio wave? It is the E field. Okay, remember that. So what determines the polarization of a radio wave? is the electric or the E field that determines the radio, what type of polarization it has. Okay. Are you happy on the basics so far of a radio wave? Yeah?
Yes.
Yeah, so just remember, waveform, complete one full cycle. Amplitude is from the top to the bottom, and that basically represents voltage or power. Frequency is the number of complete waveforms in 1 second. And frequency is calculated by the speed of light divided by the wavelength. Okay, speed of light divided by the divided by the wavelength. Makeup of a radio wave. Okay, there's 3 parts. There's the E field, the electrical field, the H field, the magnetic field, the areal, which is the direction of propagation. We now need to know the relationship between all 3, and it's 90 degrees to each other. So the E field and the H field are 90 degrees to each other, and both are 90 degrees to the direction of propagation. And what determines the polarization of a radio wave? It is the electrical or E field. The electrical or E field. Now, there's 3 types of waveform we're going to look at. Oh, everything's, come on. Go back. My pointer's stuck. Right, gents, we'll go for it. My screen's completely frozen. I can't move it. I'm going to have to come out and come back in again. So it's 10:05. We'll go for a 15-minute break and we'll come back in again. See if I can get out of this.
Okay.
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 Right, let's try again. I still can't get my pointer. That's better. Better. Hello, gentlemen.
Hello.
Hello, everything's working again. Just shut the PowerPoint down and start again. Okay. So we're going to look at the different types of radio waves we have, okay? There's three main types here. We can look at it as ground wave, sky wave, and direct wave, okay? There's only two used in civil aviation, okay? That's direct wave and sky wave. Ground wave is basically, well, ground wave is mostly used by the military, except for if you've got a long wave transmitter, but we don't use it in civil aviation, okay? So ground waves we don't use. Direct wave, okay, direct wave. The first thing to say about direct wave, it must be line of sight, okay? So a direct waveform must be line of sight. So you should be able to see the transmitter, okay? So if you've got a TV transmitter, you'll see it, and that is VHF. We've got two types of waveforms we use in direct wave. It's VHF and AM, medium wave. Okay, so FM and AM are direct waveforms. So remember that AM and FM are direct waveforms. And another name for AM is VHF. It's a very high frequency. Yep, so you see there. The next one is something called a sky wave, okay? And a sky wave, it travels through the atmosphere. It actually uses the atmosphere to travel around. Oh. And how a sky wave works, and you've all heard of it. So here's my Earth. Yep, here's my Earth. And round this, I have the ionosphere, okay? And it's basically, I can actually use, there's Britain, and all the way around here, okay? There you go, by the Himalayas, there's Nepal. And using a sky wave, which we know better as HF, high frequency wave, what the transmitter can do is the waveform can bounce off the ionosphere and actually land in Nepal. So that's an HF. Those who have listened to, and again, HF is another name for HF, is called shortwave radio. If you've ever listened to shortwave radio or HF, sometimes the signal's not very good. It basically breaks up or gets very, very quiet. And that's due to the fact that the ionosphere at night time goes further out and at daytime comes in. So HF waveforms actually, so Nepal, in fact, you're listening to, let's say the old British World Service on shortwave, you'll actually find out there will be at least 6 frequencies for you to tune into, because the ionosphere can move up and down. Therefore, the waveform might hit here, or it might hit. The waveform might end up hitting here, or it might end up hitting there, and you wouldn't really hear it. So, a form of sky wave is HF. So, sky wave, okay, uses the ionosphere. Yeah, and that bounces round. And we know that is HF. Direct wave, okay, there's you with your little radio. There's the transmitter. It's what we call line of sight. So you must be able to be in line, which is why sometimes if you go around buildings, around mountains, you can't hear AM or FM. So the two frequencies we are going to talk about is AM and FM. Okay. So my two direct waveforms are AM and FM. And my sky wave is HF, and that can travel around the world, okay? And with sky wave, why do sometimes you not hear it? It's because the ionosphere will go in and out between day and night. Now, here is the radio frequency spectrum, okay? It goes from 3 Hertz to 3 gigahertz, 300 gigahertz, okay? And it goes up by factors of 10, 3 to 30, 30 to 300, 300 to 3,000, 3,000 to 30,000, etc. Okay? Remember, this is a civil aviation course, okay? It's a civil aviation course. So this particular one here, right? That's only used by the military, okay? If you've watched some of the films, that's the frequency they use to talk to submarines. Again, military, top high frequency satellites. The area where we work in, okay? The area we work in is here. HF, VHF, and UHF, okay? And there's the frequencies of HF, VHF, and UHF, okay? You could be asked, okay, and as it says in your notes, the majority of avionics substances described in these notes fall between low frequency and UHF, okay? What I'm going to tell you now is basically between medium and UHF. Please listen to this before I say what I'm doing. You could be asked anything in this book. Okay, you could be asked what the frequency of super low frequency is. You could. But remember, gentlemen, this is a civil aviation course. All these extra stuff are used by non-civil aviation authorities or systems. HF we've talked about, VHF, okay, and that is basically where our AM and FM lie. UHF, it's very, very similar to AM, okay, it's just higher than your AM frequency. UHF for radios, we use it in some of our navigation systems. We'll talk about that later on. UHF is basically that frequency is kept for the military and police and Coast Guard, etc. And for like search and rescue. So the boys, those who are on helicopters, if you're doing search and rescue or your police helicopters, you would use UHF, okay? So you are required to know frequencies, okay? You are required to know frequencies, and that's a lot to remember. But as I keep saying, this is a civil aviation course, okay? It's a civil aviation course, and the civil aviation frequencies go from medium wave, HF, VHF, UHF, okay? But the three main ones we use in aircraft are HF, VHF, and UHF, okay? But you could be asked any of the frequencies. But please remember, it is a civil aviation course. There you go. The biggest, strongest radio wave you're going to get, lightning. That's why when you get a lightning storm, your TV and your radio signals get blotted out, because that produces a very, very big electromagnetic pulse. Right. Next thing we need to look at is how there's radio waves, that's fine. Radio waves have been going since the creation, okay? So radio waves around us, they're naturally occurring. But what we need to do is what I'm doing to you. I'm talking, or I'm going to pass information. So I need to put my voice onto a radio wave. So we're going to have a quick look at how we put a voice onto a radio wave, okay? And we call that modulation. So putting a voice or data onto a radio wave is called modulation. Right. There's two types of modulation. There's AM, amplitude modulation, and FM, frequency modulation. And when you look at your radios in your house, you've got AM and FM. And we'll look at how each one's done, how each one's created, and why and where we use each one of these. Now, the first thing we need to think about, gentlemen, okay, you've all been in the cockpit. You've all seen the radios in the cockpit of an aircraft. And when you see in the cockpit, you have the dial. It'll say, you dial it up to 173.65. Okay. That is the radio wave. Okay. That is the radio wave. It's going to leave the aircraft. But we also call that the carrier wave. So when the pilot dials in a frequency into the radio, he's dialing the carrier wave, the waveform or the frequency or the wavelength of the radio wave is going to carry our information. Okay, so that when you dial it up, that's the carrier wave. And we're going to look at amplitude modulation, how we create a voice on that, and we'll look at frequency modulation and how we put a voice on that. So let's look how we put this voice. Okay, my voice is basically shock waves. Basically, I'm forcing air molecules out. So I need to convert this analog signal, me talking, I need to convert it into an electrical signal. And here it is. You've all got it. I've got one in front of my computer. It's a microphone. Okay. A microphone is known as a transducer. Okay. A microphone is known as a transducer. So how does it work? In a transducer, the front of it's got a very thin, okay, diaphragm, plastic PVC. But when my voice, okay, my voice waves hits it, you can see here there is a magnet, okay? And that magnet is inside a coil of copper, a coil of wire. And if we now know from basic module 3 that when a magnet moves inside a conductor, it produces a waveform, an AC waveform. Okay, so how do I convert my voice into an electrical signal? It's by a transducer, otherwise known as a microphone. So let's look at how we get a AM radio signal, okay, an AM radio wave. So as we said, here's the carrier. Okay.
Ian.
Yes.
Can you please again explain this audio conversion modulation?
So is my waveform, okay, my voice, the voice wave, the air pressure, okay, hitting this transducer. If you can see here, yep, okay, oops, there's a magnet. Okay. And that magnet is in a coil of wire.
Okay.
Yeah. And if we know from our basic electrics, when a magnet goes back and forward in a coil of wire, it produces a AC, it produces a voltage. Okay, happy with that, Pakesh?
Yes, yes, yeah.
Lovely. So we look at the two parts. The carrier wave, okay, that's what the pilot, the frequency that the pilot dials into his radio selector box. Okay. So that's what the pilot, the frequency, the numbers he dials into his radio wave, his radio box, his radio selector box. This modulating wave, let's call that my speech. So when I talk, okay, I'm going to hit this microphone, and this microphone is going to produce an AC, okay, an AC waveform. And what I can look on here is and say is, looking at this waveform, if I'm speaking very loud, I've got a very, very large peak. Remember I said amplitude could be said to be power. So if I'm speaking very loud, it's very powerful. So the amplitude of that waveform's high. If I'm speaking very small, I'm speaking very quiet, the amplitude is very small. So what we're going to do is now, and this is how my amplitude modulation works. It's looking at my speech and it's actually increasing the amplitude, or I'm very quiet, it will decrease it. So what we're going to do, that's my carrier wave, that's the AC waveform or the modulated waveform from my voice. I put them together, okay? I put them together and we get what's called the modulated waveform, okay? And in this case, this is called AM. And if you look at it, it's the amplitude of the waveform it changes. The frequency stays the same, okay? So in AM or amplitude modulation, how is speech, how is the waveform transmitted or the information transmitted? It changes the amplitude of the waveform, but not the frequency, okay? So in AM, we change the amplitude of the waveform. And here's a basic block diagram, okay? All you're going to be asked is what are the 4 parts of a basic radio wave? The microphone, which is my transducer, the RF oscillator, that basically that's your radio carrier wave. We put it into a modulator, okay? We bring them together in a modulator and we send it to a antenna or aerial for it to transmit. So you do need to know the block diagram of a basic radio system. Microphone, RF oscillator, into a modulator, out to the antenna. Now, you've probably seen in the cockpit in the VHF. Now, AM, okay, the other name for the AM in aircraft is VHF. So AM equals VHF. And when you look at the VHF radio selector box, you've got the frequency dial, yep, and you've actually got a little switch that will say USB, okay, and LSB. Somebody's starting the car up. Now, if we look at here, now remember, we'll get 2 VHF aerials, one at the top, one at the bottom. Now, if I got to send the whole of this modulated waveform, okay, if I've got to send the whole of the modulated waveform, okay, so the whole bit down here, I'm having to send the carrier wave, this whole waveform. That takes a lot of power, okay, takes a lot of power. So what we actually do is we're going to look at how we can save power or use the same amount of power and send the radio signal further, okay, send the radio wave further. So we look at the 3 parts of a VHF or AM signal. So this is a AM radio wave. So there's my carrier wave. That's the frequency we have sent it out. And then we have the upper part of the modulated waveform and the bottom part of the modulated waveform. Now, gentlemen, that's the complete waveform. Can I say that the top part is a mirror of the bottom part? They basically got symmetry. So what we're actually going to do, we're only going to send half the waveform, either the upper or lower sideband, depending what the pilot selects. So what I intend to do is I'm only going to send one of the sidebands, okay? That's what we call half the modulation is a sideband. We'll look at, but you're going to say to me, Ian, I'm only sending half the information. And I'm going to say you are correct, okay? You are correct. But as I've said, the bottom half is a mirror of the top half. So when we look at how we collect that information, when I receive an AM upper or lower sideband signal, I'm only getting half the message. But electronically, the VHF or AM receiver electronically puts the other half back on, and we'll look at that later on. So there's my carrier wave, and there we've got the bandwidth. Okay, the upper and lower sideband. So what we're going to do, not only am I going to, once I've created this modulated waveform, okay, when I've created that modulated waveform, that's what it looks like. I've got my carrier wave, the lower sideband and the upper sideband, okay. And that diameter, that amplitude basically determines the bandwidth, the amount of space it takes up in the atmosphere. So now I've had to use a lot of power to create a carrier wave and an upper and lower sideband, but the radio wave still, the AM radio wave still hasn't left the aircraft. To send all these three parts of this radio wave takes even more power. So what we're actually going to do is only send one of the sidebands. In this case, we're going to talk about the upper sideband, and it has two advantages. One, I'm saving power because I'm not using power to send the lower sideband, and I'm not using power to send the carrier wave. I'm only using power to send the upper sideband, half the message. So when I send a single sideband radio message, I have saved power, and I've reduced bandwidth, okay? So what is the advantages of in a AM radio wave sending only a upper or lower sideband? I'm saving power, and I'm actually I'm reducing the bandwidth of that radio signal, okay? I'm saving power and reduced bandwidth, okay? I've reduced bandwidth. So that's AM. Next thing we're going to look at is FM. Okay, FM radio. Again, there we go. I have my carrier wave. That is basically the exact same. It's what you dial into your radio to send the modulated waveform. So the carrier, that's not changed. The modulated waveform, that's not changed. What has changed is how we put them together. Okay, how we put them together. And if you look at the resultant modulated waveform, you can see that the amplitude of the waveform stays the same. But what has changed is the frequency. So in FM, my voice, when I talk very soft, I have a large frequency. The frequency increases. When I talk very loud, the frequency becomes smaller. Okay, increase the frequency range. I can increase the frequency when I become louder. I decrease the frequency when I become quieter. So in FM radios, what changes is the frequency of the waveform, not the amplitude. Okay, in FM and frequency modulation, how is the radio wave sent? The amplitude doesn't change, the frequency changes with the voice or the data on it. Okay. Now, let's look at the two radio waves. We have AM, where we've actually halved the information, okay? Half the information. And modulation, okay, increasing the frequency. Gentlemen, you've all got in your cars and your houses, you've got an AM radio and an FM radio. Which one of the two has the best? Which one of the two has the best reception? You can hear the music better. Is it AM or FM?
It's AM.
AM? Or is it FM?
It's FM.
FM's got the best reception. AM could be not good, and sometimes it might become soft and loud. So FM, okay, is the best reception. Yeah. It's the best reception. Have you got an FM radio in your aircraft? Anyone? No. Have you got an AM or VHF radio in your aircraft? Yes. But we've already said that frequency modulation radios have a better reception, so you can hear the voices of the songs better. So why don't we use FM in our aircraft rather than AM? Okay, well, here's the first thing. FM has a very large bandwidth, 180 kilohertz. And I'm going to say in our aircraft with VHF, it's 8.33 kilohertz. So for one channel, okay, one channel of VHF, I can get nearly 90, I'll get 19, I can get 19 into one FM. Okay, so you think about it, aircraft are only given so many channels to communicate with. And if I can get 20 VHF for one FM, that's why we do it. So basically, we can get more channels in AM than we can in FM. So let's look at, so that's the first thing. Why do we use AM rather than FM? It's basically I can get more channels into one channel of FM and get nearly 20 channels of AM. Now,
So then,
yes.
so you mean to say that in FM there's a large bandwidth, that's why we are unable to use in the aircraft?
I didn't hear what you said there.
Due to the large bandwidth requirement, we cannot use the FM, that's why?
That's correct, yes.
Okay.
Okay, even though it's the better quality, we can get more channels, okay? And we're going to look at quality of the signals now and why it is. So let's look at let's look at the two waveforms and how it works. Now, if I was to look at the waveforms of AM and FM under an oscilloscope, I'll look at the top there. Yeah, what it actually looks like is this. It's got lots and lots of spikes. And that is my AM, amplitude modulation. So what in AM, I'm actually looking at the amplitude of the waveform to give me my voice. So now if I've got here the AM signal and it's got all these spikes, that is why AM is not as good. If I look at FM, it's only measuring the frequency. It's only counting the frequency. And if I count the frequency at where it crosses the 0 point, I'm not picking up any distortion. And that is why FM is a better quality signal than AM, okay? Even though we're going to use AM. So you have to understand, why is FM a better quality signal than AM? Because FM is only measuring the counting the frequency, where AM is measuring the amplitude, and at the top of the amplitude we have that distortion, all those spikes, which causes my signal to be distorted. Okay, so that is radio waves. That's why we use, why FM is better than AM, though we're only going to use AM in our aircraft. And the reason is I can get nearly 20 AM channels for one FM channel. Okay, we look at the basics of a simple system, okay? So each system has to have a transmitter and receiver, okay? Each system has a transmitter and receiver. We've been through this already. The simple AM transmitter, microphone, modulated waveform. RF oscillator, that's my carrier waveform. We put them together in a modulator and then we send the signal out. But now if I want to send that signal further, I will put it through an amplifier. So in reality, the only change from the basic radio system is we boost the signal, we give the signal more power. So that's speech. And that is carrier wave. That's where the two are put together, the modulator, and that's basically boosting the signal to send it out. Okay, so that's the basic block diagram of an AM transmitter or VHF transmitter. Now we're going to look at the receiver, okay? A simple receiver. We're just looking at if I'm going to send the whole message, okay? Both. I should receive the AM waveform. It is probably very, very weak, okay? It might be as low as 1/4 of a watt. Very, very little power. Therefore, I have to amplify it. I put it through a detector. Okay, sometimes the detector is called a demodulator. And what I'm doing is, I'm taking away the carrier waveform. If I take away the carrier waveform, I'm left with that modulated waveform. Then I'll amplify it and put it in the speaker of my headphones. That's a basic, simple one. But let's look at what happens. Okay, let's look at what happens in reality. As we said, that is my AM signal, but we only send the either upper sideband. Okay, upper sideband. So what this detector stroke demodulator also does, it puts in the other half of that waveform because it's a mirror. So when it comes out, we get the modulated waveform. Okay, so that's what happens in the AM receiver. It electronically puts the other half, the other sideband, onto the modulated waveband. Then we take the carrier wave frequency out and lasers with the modulated waveform. Okay.
Hello, Ian.
Yes.
Hello.
Yes, I'm listening.
Can you please again explain that that detectors?
Get that there?
Okay.
Okay. So I'm receiving the signal. Okay.
Okay. Okay.
Let's talk about it as the signal we're going to get in. Okay. So in reality is I'm going to get this. Yep. I'm only going to get half the waveform. Yep.
Okay.
Yep. So reality is that's what I'm getting. So we're not going to see that. We're just going to see one of the sidebands. Yep.
Okay.
Agree with that?
Okay.
Yep. But it doesn't matter when it arrives. It's very, very weak. Okay. There's very little power. So I need to put it through an amplifier to boost the signal. Yep.
Okay.
I then put it through this demodulator. So the demodulator takes away two things. It takes away the carrier waveform. Yeah, so it takes out carrier wave, but adds the other half of the waveform electronically. Yep. So coming into here, I had this signal. But in here, I'm going to take out the carrier wave. Okay, I'm going to take out the carrier wave, but add the other half of the waveform. So electronically, I add the other. Oh, for goodness sake, give me a break. Yeah. So I electronically add. Okay, we got the upper side band. I'm electronically adding the lower side band, getting a speech. Again, that is quite not very powerful. So I'll put it through an amplifier to put to the speakers or to the headset. Okay, so that's what happens in that detector. It takes away the carrier wave and adds the lower side band so I can get the full message. Okay, does that make sense?
Okay. Thank you.
No problem. Okay, let's look at aerials. So, aerial. In reality, okay, if I want to send all of my signal, I really want to have the aerial as long as the wavelength of my radio signal, okay? I really want to send the wavelength of the aerial. Now, one of the frequencies we talked about was HF. HF is 3 to 30 meters. Have you ever seen an aerial that's 3 meters, never mind 30 meters on an aircraft? No. So what we can do, okay, what we can actually do is we can actually send a fraction, or we can have the length of the aerial a fraction of the wavelength, okay, of the waveform. So what we can actually do is, again, if you look at your notes, ideally, okay, so give me a break. My ideal length of my aerial should equal the wavelength of radio wave. Yep, that's the ideal. But the problem is we can't have those lengths. But what we can do, okay, is we can send a fraction. So we can either send half or a quarter of that wavelength. So my aerial can either be half or a quarter of the wavelength of the radio wave. So what ideally I should have, if I've got a 30 meter wavelength of radio wave, I should send 30 meter, I should have a 30 meter radio aerial. But what I can do is I can actually send my aerial can be a full fraction, either a quarter or a half of the length or the wavelength of the radio signal. So in reality, the actual length, okay, so the actual length of my aerial equals a quarter of the wavelength. So remember that statement there. What relationship do we have to the antennas or aerials? It should be the aerial length should be a quarter quarter of the length of the waveform. And if you actually look at in your notes, it gives you an example. It says a frequency of 150 megahertz has a wavelength of 2 meters. So a quarter of the wavelength, the antenna is 50 centimeters. So 200 centimeters, a quarter of that is 50. Okay. So remember that relationship between the wavelength of the radio and the length of the aerial. Okay. Please remember that relationship. Okay. There's several different types of aerial out there. This one here is what we call a whip aerial. And the waveform goes out, okay? If I look at that, it actually looks more like a donut, okay? So don't worry too much about on the shape, but all you need to remember is the length of the aerial in reality must be quarter the wavelength, okay? Must be quarter the wavelength. Okay, we're happy on aerials. Not a lot to remember about it, just basically what I've been telling you. And happy about the basic makeup of a transmitter, which is a modulator, an RF modulator, microphone, oscillator, produces the carrier wave. We put them through a modulator, we amplify it and send it out. When I receive the information from my aerial, it's very, very low powered. I have to amplify it. I will put it through the detector or demodulator. I will then amplify it, and that will go to my headphones or microphone, loudspeaker. Right, gents, any questions on that little bit we've just done? No? Right, next bit we're going to look at is the specific communication systems we've got on our aircraft, okay? It's not complex, there's just a bit of information to remember, okay? It's not complex, and it's just a bit of information to remember. And again, I will be going through it with you, okay? I'll be going through it with you. We're going to take a 10-minute break, and then we're going to start again, okay? I will see you in 10 minutes.
Okay.
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 Hello, gentlemen. Can you hear me?
Yes.
Oh, okay. It just seems to be on my. Oh, it's also back up now. Good, lovely. Okay, I'm going to be doing a lot of digging. It's a massive big blizzard outside. The snow. I think the snow must be not far off being up my knees. I'm going to be all hot and sweaty when I come back after lunch. So I've got a couple of old ladies now next door to me, so I'm going to have to clear their paths as well. Oh. Okay. Right. Any questions what we've done this morning so far? Anyone? Before we go on. Yes.
In the antennas, in our notes, it's mentioned that the vertical mounted antennas will receive the vertically polarized signal. What does that mean? And horizontal will be horizontal.
Okay. Remember we talked about the signal, the waveform. Remember the radio wave is made of two parts. Remember that? E field and H field?
Yeah.
And we said that the radio wave can be either vertically or horizontally polarized, and that will depend on the
E field.
E field. So it's very difficult for me to draw, but basically it either means that's, let's say if I do my waveform like that, okay, and it's straight up and down, that means it's vertically, okay, vertically polarized. If it goes snakes, or it's very difficult for me to draw something horizontal in a page, but you can see if it goes sort of horizontally, I can't draw horizontal.
I understand.
Yeah. So basically, it's how the aerial. So let's go back. We'll just make sure we're all happy with that. So let's just go back a bit to aerials. Okay. Let's look at this aerial here. This is me looking down on the aerial. Okay. So, in fact, let me phrase it. Let's me say that now, that aerial is on its side. Think about your TV aerials, the terrestrial television aerials you have on the top of the houses. And you do see these aerials. Some are actually got the little spikes straight up and down, and some of them have got the aerials with a flat horizontal. So what I can actually say, looking at this, okay, at this aerial, my waveform must be vertical, because you can see it's on its side. So basically, that aerial must receive vertically polarized radio signals or TV signals. This one here, you can see it's on its side. Okay, so basically what's going to happen is the waveform is going to snake horizontally. So my waveform is horizontally polarized. So this aerial here, the vertical polarized one, it cannot receive horizontally polarized radio signals. And the horizontally polarized aerial can't receive vertical polarized radio waves. Now, have a think about that. Have you ever looked, Chris, what are the aerials like, the TV aerials, like on the top of the roofs in Kathmandu? Are the spikes standing up, or the spikes horizontal?
Horizontal.
Horizontal. Yeah. Okay. So the television transmitter putting out your TV signal is sending out the TV radio signals horizontally polarized. But if you go down further down the valley, to one of the towns or cities down the valley, if you look at the aerials in the next towns, their aerials would be vertically polarized. Because what you don't want is the two TV signals to hit each other. So if you're a town that's halfway between Kathmandu and the next big city, you might be able to pick up both TV signals. And if you could, you get two pictures. So what you actually have is that one city will have horizontally polarized aerials, and one city, the next city, will be vertically polarized. So the signals can't cross over each other and get like two pictures on the one TV screen. Does that sort of answer your question, Chris?
Yeah, thank you.
No problem. Right. Anyone else get any questions of what we've done so far? Okay, good. So the first communication or radio system, the three systems we're going to look at is the common communication systems in aircraft. And you notice I didn't say radio systems, I said communication systems. Anything that allows us to talk to anyone else. And the first one we've talked about already is VHF. The other one we're going to look at is HF. And the third one we're going to look at is satellite communications. Okay, satellite communications. So we're going to look at the three systems that allows us to talk to other aircraft, us to talk to our airline operation centres, and to talk to air traffic control. Communications, up until very, very recently, relied on voice. Communications, up until very, very recently, relied on voice only. So when you were approaching Kathmandu, you would call up on HF. So let's say you were still in Indian airspace. You were about 5 or 6, 1,000 miles away. You would call up on HF and you would talk to Kathmandu saying, what's the weather like? I'm coming in at this time. And as closer you got, you would then go into VHF. And that was it. But as we go on now later on, gentlemen, we'll find out that some of these communication systems, not only can we send voice messages, we can now send data. We can actually send data messages. Okay, and we'll look at why that is an advantage when we come to these systems. So the three communication systems we're going to look at is VHF, HF, and we're also going to look at satellite communications. Okay. So VHF, very high frequency. Okay, VHF. I remember we said we also called VHF AM. So another name for our VHF is AM. Okay, amplitude modulation. But in your aircraft, we call it VHF, very high frequency, because it's in the VHF frequency band. Okay, which I believe is 30 to 300 kilohertz. Is it kilohertz or megahertz? Megahertz. So let's look at the basic system. Okay. This would be the basic system you'll find in smaller or older aircraft and maybe some of the helicopters you've got out there. Let's look at the main part, okay? Here's your transmitter receiver, your control unit, your radio control box. And that is where you will dial up the frequency. There's your frequency button, and you would tune into the frequency. We'll look at frequencies in a minute. You'll tune into the frequency, and that'll allow you to talk to and listen to everyone on that frequency. And that's also got your volume. And if you look here, we have two little windows, okay? Most aircraft now, there's some sort of LED, though some older aircraft might be. It's a rotary switch with painted numbers. And it says there we have active and standby. Active and standby. What this allows us to do is tune in two frequencies, okay? Two frequencies. Why would we want to be able to tune in two frequencies? Well, let's have a think. Let's think about, I'm coming in to land at Kathmandu Airport, okay? So I'm coming in to Kathmandu Airport. So the first thing I'm actually going to do is I'm going to talk to Kathmandu approach, okay? So what I'm going to do is I'll dial that into the active frequency. So I'll dial in the frequency. Let's call it colour. Okay, let's call it 123.65. So that is the frequency for Kathmandu approach. But the next frequency I'm going to be going on to is Kathmandu radar. Okay, and that might be 133.75. So now I'm talking to approach. And they're going to tell me, yes, we know about you coming. Here's the weather. Okay, you're going to be landing on this runway. And then, once we get close to Kathmandu, the approach will hand us over to the radar. Okay, so the frequency for the radar. And all we need to do is, we've already got that in standby. And what you've actually got, you see a little switch here? All you do is press that, and that will make the standby frequency the active frequency. So now I can talk to the radar. So while I'm talking to the radar, when I land, I know I've got to talk to the tower to make me land on the runway and taxi off. So what I can do, while I'm talking to the radar, I can put on 1695. I can put in the tower. As soon as I land and I need to start taxiing, I can press that button to that side and it allows me to talk to the tower. So I don't have to have a time where I'm not changing over frequencies. I've got the next one always set up. So that's why we have an active and a VHF controller. We've usually got two frequencies. One is for active and one is standby. So that's the controller, the transmitter receiver. And in smaller aircraft, it is actually one unit. There's my headset, and there's my VHF aerial. And that's going to be some sort of coaxial cable. And that'll be some sort of coax cable. Next bit, we have our power. That goes without saying. And then we have our press to transmit. It'll either be a button on the headset. You might have, for smaller aircraft, the old buttons. And some aircraft, especially the helicopters, you have a press to transmit button on the floor, because sometimes the pilots have got both hands full. Is that correct, gentlemen? Those who are the helicopter boys, have you got a press to transmit button on the floor of the helicopter?
In the cyclic?
Yeah, one in the cyclic. Have you got one on the floor as well?
No, not at the floor. Only in the cyclic.
Oh, only cyclic, right?
Yeah.
Okay. Some other helicopters actually have it. Another button on the floor as well. It doesn't matter. So that is the basics of my VHF. So basically, I have a transmitter receiver, I have a headset, and I have an aerial. Now look at a complex. This is going to be what you're going to find in your modern aircraft. So now the control unit doesn't send out any messages. That is just a box to dial in the frequencies. Okay, 127.65. Yep. All that's doing is dialing the frequencies and controlling the volume. Yeah, that's all it's doing nothing else. And now everything is going to be sent to a transmitter receiver. This is going to be in the avionics compartment of your aircraft. It's not going to be in the cockpit. So that'll be in the avionics compartment. This information is now going to be digital, a whole load of ones and zeros. But this bit here is the same. Again, it's coaxial cable. We use coaxial cables for all transmitting of high or radio signals, okay? But if you actually look at the basic block diagram again, it's not that different. We have a control unit, but this time it's separate to the transmitter receiver, and you have an antenna to send the signal out. So in reality it's not much difference. It's just now, will all your aircraft now be flying computers? Okay, all your aircraft being flying computers, it's going to send a lot of data, like the frequency it wants, and the information is going to be digital, i.e. computerized. Now, there is information here on foot. We're going to go through it, okay? Just listen to what I'm saying. Now, in your notes, now, unfortunately, gentlemen, throughout time, the guys who deal with radios and radars always deal with frequencies, okay? Frequencies. So even when you go and start doing some type courses, they will be looking at frequencies that you may have to remember. So when I talk about a frequency, you might be asked to remember the frequency range of these radios, okay? And VHF, according to your notes, says VHF is 118 to 136.995. That's what your notes state. Is that correct, gentlemen? Anyone got the notes in front of them?
Yeah.
Yeah, is that what it says?
Yeah.
It says 136.995. It's a difficult number to remember. Everyone remember VHF is 118 to 137 megahertz. Okay, so if you can remember, VHF is 118 to 137. Yes, Prakash. Oh, I think your hand up there, Prakash. So you do need to be able to understand or be able to tell what the frequency of VHS. If you just remember 118 to 137, it's a lot easier than 136.995. Everyone who is an avionics technician will remember VHF is 118 to 137 megahertz. The next thing is, it is a low-powered system, okay? It's a low-powered system. Remember what I said is, it's a direct line of sight, okay? It's only a line of sight. So basically, we're only going to use it in a close area, okay? We're only going to use it in a close area. So that's why it has a power of 25 watts. So a VHF is a low-powered line of sight, okay? Low-powered, 25 watts. Next thing is range, okay? Range. It says here 250 miles at cruising altitude. So let's have a look at what that means. Okay, there's my ground. There's 30, let's call it 36,000 feet. And there's Kathmandu Tower. It's a low power. So let's imagine now, there I am with a VHF walkie-talkie. I might only get 3 to 4 miles. If I stand on top of a house, I might get 12 miles. If I stand on top of maybe a 2 or 3 story building, I might get 25 miles because it's line of sight. Yep. But when I'm at 36,000 feet, okay, that range is extended to 250 miles, okay? So what is the range of VHF at cruising altitudes or 36,000 feet? It is approximately 250 miles, okay? 250 miles. Next thing, if you've got a channel selector for VHF, okay, each channel has a frequency range of 8.33 megahertz. Okay, so each channel, so that's not megahertz, sorry, it's kilohertz. So it's 8.33 kilohertz, okay? So the channel spacing is 8.33 kilohertz. That's only just recently changed, gentlemen. There used to be 2 spacings, it's now gone down to 1. So you can now see when we said we had FM was 180 kilohertz per channel. Look here, I've got 8.33. So I said, you've nearly got 20. And the next thing, okay, is to remember. Now, when you remember it for the exam, or you remember it because it's a good bit of information to remember. Okay, it's a good bit of information. It's called the International Distress Frequency, otherwise known as the guard frequency. Anyone ever heard they talk about the guard frequency? Anyone? No.
No. It's a
No.
kind of reserve frequency, right?
Pardon?
It's a kind of reserve frequency.
It is. It's a distress frequency. This frequency, okay, every aircraft, when it's flying about, its system is designed to monitor 121.45 megahertz. Every air traffic control centre will measure or will listen for 121.5 megahertz. Every ship that sails the ocean also listens to 121.5 megahertz. Every military radio, so all your military radios, okay, all your military airports, all measure or all listen to 121.5 megahertz. So remember what the international distress frequency is. It's also known, you might hear the pilots talk about guard frequency. No one talks on that frequency unless it is an emergency. Okay, so what you'll find is if an aircraft has an engine failure, okay, it will go to 121.5 and he'll tell the tower he has an engine failure. No one, the only people will be talking to him will be the tower and that aircraft, no one else. Okay, other aircraft can hear it, no one else will be talking on it. So, gentlemen, if you ever have to go and do a radio check, okay, the one channel you must never, ever, ever use is the international distress frequency of 121.5. Because, gentlemen, I don't know what, it'll be very similar, take it to what happens in the UK. If you use that frequency, there'll be a car with a blue light on top of it with police officers inside coming to take you away in handcuffs. Okay, so what frequency must you never do a radio check on is the international distress frequency, which is 121.5. Okay, 121.5. Do not transmit on that. So if you take anything away this morning, that there. And of course, also, if you're in a helicopter, an aircraft that makes an emergency landing and the pilots are injured or can't, if you know how to get that frequency, you can call up the emergency services. Okay, so to highlight what you need to know in VHF, well, reality is, gentlemen, it's all on that page. 118 to 137 megahertz. That's the frequency range. It's a low power, it's called a low powered radio system, 25 watts. It has a line of sight communication range of up to 250 nautical miles at the cruising altitude of 36,000 feet. Each channel is spaced by 8.33 kilohertz. And the international distress frequency is 121.5 kilohertz. Okay. Remember that information about VHF, it's on that slide. Any questions on VHF?
What is this? Hello, Ian.
Yes.
What is this channel spacing means?
Basically, for every channel, okay, so if I have a frequency, let's call it, if I have a frequency, okay, or the best way is bandwidth, okay? What we're actually talking about channel is the bandwidth. So the bandwidth is 8.33 kilohertz, yep. So that's the bandwidth. So between each channel, so if that's channel 1, that's channel 2, I've got a bandwidth of 8.33 kilohertz. So channel 3 is 8.33 kilohertz. Yeah. So you can actually see if I'm at megahertz, how many channels I can get. I can get hundreds of channels, but not all of them are allocated to aviation. Okay, you've got all your radio stations, you've got those using walkie-talkies, you've got TV, you've got ships. So we're only allocated so many of these channels, okay? So that's what we're actually meaning by a spacing. So basically between each channel, so when you look at your VHF selector box, you'll have a switch. You can have up to 20, I think it's 25 pre-selected frequencies. That's 25 channels that your aircraft has got selected. But it doesn't mean it can tune other frequencies manually, but you'll have 25 pre-selected channels. Okay? Does that answer your question, Prakash?
Okay, thank you, Ian.
Okay,
Yes.
no problem. And the next bit is the international distress frequency 121.5 megahertz. Please remember that. Okay, please remember that. So VHF was line of sight. Next one we're going to talk about is HF. HF is a worldwide communication system. I have actually been in the Indian Ocean in a helicopter about 5,500 feet. We tuned into the HF and I managed to talk to the radio station, okay, at my airport in the UK. Okay, so we're talking thousands of miles. So an HF system, okay, is a worldwide system. The downside with HF is it also can be affected by what we call atmospherics, the ionosphere. Okay, so HF, that's the first thing you need to take out of this. HF is a worldwide communication system. The downside is it, okay, it's not 100% reliable, because things like when the ionosphere, there's my Earth's surface, there's the ionosphere, and as I said, it's a sky wave, so my radio wave goes and bounces down from the ionosphere. At night time, the ionosphere goes out. So if I'm talking to, let's call that, I'm talking, there's London, there's Kathmandu. In the daytime, that is the frequency to talk to Kathmandu. But if I use the exact same frequency, oh, I didn't plan that. If I use the exact same frequency, it wouldn't hit Kathmandu, because basically the ionosphere is, in fact, let me do it again. So with the ionosphere, what happens is it comes up, comes back down, comes up, comes back down, and you can see there the wavelength changes. So that radio signal will not get to Kathmandu. That's why when you actually look at HF, each radio station will have 6 frequencies. So basically, so Kathmandu will have 1, 2, 3, 4, 5, 6 HF frequencies at Kathmandu Tower. Some for the daytime, some for the nighttime, and some for different in between. So that's one reason why it's not reliable. The next thing, if I get a thunderstorm, it'll block it out. When we fly at very high northern latitudes and very high or very low southern, like flying over the North and South Pole, has anyone heard of the things called the Northern Lights? Anyone? Aurora Borealis? Well, what happens up at very high latitudes, the solar winds, the charged particles from the sun, cause the atmosphere to become charged. Okay? And you get all these green, pink, and purple and white lights. And they basically destroy the HF. So that is why HF is not very, or can be not reliable. It can depend on weather and the atmospheric conditions and the time of day. Okay, so HF, the first thing is two things you need to remember so far. HF is a worldwide communication system. The next thing is it's not 100% reliable due to atmospheric conditions, weather, etc. Okay. Oh, it's 1 o'clock. Right. What we're going to do now, we'll go for a break for my lunch and your dinner. Okay. We'll go for an hour, and then we'll come back and we'll learn about the HF system. Okay. So back in 1 hour. All happy in that?
Okay.
Okay, lovely. I will see you in 1 hour.
Okay.
I'm going to go and shovel some snow.
Okay.
Thank you. Oh, hello, gentlemen. Hello. Can you hear me?
Yes, yes, we can.
How are you all after lunch? Well, dinner, however you what you call it. I'm all sweaty. I've been shoveling snow for about 40 minutes.
Oh, good exercise.
Yes. Yeah. All hot and sweat. I should really go for a shower, but you can't smell me at that distance.
Yeah, little bit. Yeah, I think.
Yeah. Just wait a couple more to come in. So while we're waiting, everyone happy on what we've done so far today?
Yeah, we are happy.
Good. Okay. So before lunch, or my lunch and your dinner or whatever, we started looking at HF, and the first thing we said is it is a worldwide communication system. Okay, it's a worldwide communication system, but its big disadvantage is weather conditions, the ionosphere, etc., can make it unreliable. Okay, can make it unreliable. Now, we're going to look at the HF system. It's very, very similar to any other radio system we talked about. There's your control unit, where you're active and standby frequencies, so you can change between two frequencies quite easy. Again, in the modern aircraft, we send the signals to the transmitter receiver via data bus. And then we've got the coax cable again. Can't see. And then again, we've got coax cable. And again, you can see there, I've got coax as well. And then you've got your aerial, okay? HF aerials tend to be quite big. But the fun thing is different is this thing here called an antenna coupler, okay? It's an antenna coupler. Some aircraft is not called antenna, it's called a HF tuning unit, okay? That's the name we're called, that's the official name, but a lot of aircraft, we call it the HF tuning unit. Now, we said it goes from 3, okay, HF goes from 3 to 30 megahertz, okay? 3 to 30 megahertz. I'm not going to do the calculation, but 3 to 30 megahertz has a wavelength of between 10 meters and 100 meters. Okay, it has. So you can see the minimum length for an HF cable has to be 10 meters. Okay, we could quarter that and make it 2.5 meters. Okay, or 25 meters. Okay, 25 meters is still a big difference. So that's one big aerial. Now, if you look at some of the older aircraft, they used to have an aerial outside the aircraft. It looked like a bit of black coax cable, and it was usually the length of the aircraft. That was an HF cable. Okay. But now in modern aircraft, we don't have aerials 25 meters long. So what the antenna coupler does, it artificially changes the length through electronics the length of the HF aerial. Okay, so you will have an HF aerial in your aircraft. It might be half a metre long. But what we can do is with this HF tuning unit or antenna coupler, so this antenna coupler can electronically extend the HF antenna. Okay, the HF antenna. So, not much difference here, but you will be asked what the HF antenna does, okay? Okay, so basically it artificially extends the size of the HF aerial, okay? And I think it says in your notes, it talks about the antenna size to ensure the optimum propagation, i.e. the correct wavelength. But we can do this, we can use the antenna coupler to electronically alter the size of the antenna, okay? So what's the purpose of the antenna coupler? Electronically extends the size of the HF antenna. All happy on that bit about the HF antenna. Now, when the one thing, if you're ever going to do an HF or communicate in HF, the pilots have to put in the frequency. And you see here, this little button, okay? It's called the tuning button, the HF tuning button or HF tuner. And when you press that button, you never get the HF frequency instantly. It takes several seconds because what you're actually doing is you're allowing the electronics, okay, to work to extend the aerial length or electronically extend the aerial length. So just be aware, HF, you don't instantly get the frequency. You have to select the frequency and then you have to tune the HF to that frequency by the antenna coupler. Okay. So we're all happy what the antenna coupler. Are we all happy what the purpose of the antenna coupler is? Yep. Good. Now I said this was HF was worldwide. Okay. If you get the right weather condition, atmospheric conditions, you can talk to the other side of the world. Remember I said VHF was 25 watts. So the first thing we need to think about is in HF, okay, I need more power because I'm going to go halfway around the world. So the power, okay, the power coming out of that antenna is 400 watts. It's a very powerful transmitting system. Okay. Right. Now this is just not for any exam. This is for your own safety. Every airport, okay, if you look at the map of an airport, there'll be an area where you're allowed to test the HF. You just can't drag the aircraft out of the hangar and test it, because up to 10 meters, you can get what's called RF burns, radio frequency burns. It is literally like standing. Remember, most microwaves are 800 watts. So it's like standing by half a microwave. So if it takes 1 minute to cook your potatoes, it'll take 2 minutes with an HF aerial. And none of you would put your hand in a microwave. So never ever transmit on the HF aerial if there's anyone near, and you should only ever do it in the approved area of the airfield. Okay, your operations centre, your engineering operations centres will have a map. Your avionics technicians will tell you where the map is, where you can test the HF radio. Okay, you just can't test it in the hangar, definitely not in the hangar or on the line. It has to be a specific place in the airfield. Once you're in the air, it doesn't matter. Inside the aircraft, it doesn't matter, because you've got metal. It's going to stop the radio waves getting through anyway. So far, what have we learned in HF? It is a worldwide system, but it can have problems of reliability because of weather, atmospheric conditions. Its frequency range is 3 to 30 megahertz. Its power output is 400 watts. It's a very powerful system. But because of the wavelength of my HF, frequency is between 10 and 100 meters, or even if I take the aerial at quarter, it's 2.5 to 25. That's a large aerial. So we actually fit the antenna coupler, and the antenna coupler electronically changes or extends the size of the HF aerial. Okay, let's look at this, all the sort of data. So what I've talked about there, and what we've got. So you are required to understand and remember the frequency of HF, 3 to 300 megahertz. Okay, 3 to 300 megahertz. The power, again, I've said 400 watts. It's worldwide, okay, go all around the world. And between each channel, there is a 1 kilohertz spacing, okay? 1 kilohertz spacing. Now, what do we use this for? Well, the first thing is we can use verbal communication. So we can talk to our airline operations centre. We can talk to an air traffic control centre. We talk to an airline control centre. We can also talk to other aircraft that are far away. Okay, far away. And that's what it was up until very recently. And then we brought in something called the controller pilot data link. It's a digital system. And what this does allows the air traffic controllers and the aircraft to talk to each other, but in like text. So basically, it will send a written message. So if you're, in our case, we've got 2 what we call transatlantic operation centres, one in Scotland and one in Canada. and the Atlantic's 2,500 miles wide. What you can actually do is, our air traffic control, they can actually send out the communications, the frequencies, the air lanes, how to approach Canada, all on a written or in a text format on a screen. Why is that an advantage? Well, the advantage is, if it's written, it's very difficult to not hear it correctly and forget it, okay? So we can send in HF not only voice communications, we can also send digital information, okay? We can send digital information. So let's highlight exactly what we need to know about HF. It's a worldwide comms. It's not 100% reliable. The frequency range is 3 to 30 megahertz. It has a power output of 400 watts. Therefore, it can cause radio frequency burns. Okay, so you should never transmit the HF when there's personnel present. Therefore, do it at the place where you're allowed to test the HF at the airport. It is 1 kilohertz spacing. And the only other big thing we need to think about is what the purpose of the antenna coupler is. It artificially changes the length of the antenna for the HF system. Okay, all happy on HF. It's just, remember, these are all level, you just got to quote figures or statistics or basic understanding of the system.
Hello,
Okay.
Ian.
Yes, Prakash.
Hello?
Yes. Prakash?
Only in this chapter, what important is we should only know what this antenna coupler is for. That is, it extends the range of antenna.
That's what the antenna coupler does. It's no more, no less.
Okay,
The B2s will go into the electronics of how it works. Poor them. All you need to know is what the antenna coupler does. Okay, nothing else for the Mod 11.
And Ian, there are two frequency settings, active and standby.
Yep. Basically, it allows you to set. Okay. I can have the active. Let's say I want to talk to Kathmandu Tower. I can set that there. But let's say I'm also in. I'm going to go from Kathmandu to. Let's say I'm going to fly to. I don't know where we go. Delhi. I'm going to fly to Delhi. Okay, so I'm flying down. Let's say I'm flying from China. I'm about 1,000 miles out from Kathmandu. So I want to talk to Kathmandu Air Traffic Control to say, I'm coming here. But my next place I'm going to go is Delhi in India. So I could have selected here in active Kathmandu frequency, because that's who I'm talking to. But I can also put in Delhi's airport frequency. And if you look at this little button here, that little button there, the arrow, allows me to just select which one I'm using. So I can have one talking to and I have one ready to change over instantly when I have to. Okay?
Okay. That button is there to switch from active to standby and standby to active.
Yes, I have two frequencies selected. I can be talking on one and I'm ready to talk on the next one straight away, rather than have to retune.
Okay, Ian, thank you.
No problem. Anyone else got any questions on HF? Good. Right, the third type of communication now in common aircraft is satellite communications. Okay, satellite communications. Now, if you've looked at, I know that the I don't know if any of the Nepalese aircraft have got satellite comms. I'm surprised if they don't. But most aircraft now have it. And it's no difference to what if you think about the aircraft, it's no difference than your house. Okay. There you go. There's your router. Inside the router, that's going to pick up your mobile phones or the screens in the front of your headrest. So that doesn't work any different. Now, I can actually use data or I can use voice. And there's my satellite antenna. It's usually at the top of the aircraft. And if you've seen the 777 that comes in from Dubai, there's a big lump in the top of the aircraft. That's where your satellite dish is. And it sends it to a satellite up in the sky. Okay. They're what they called, the satellites are what we call geostationary satellites. Okay. Geostationary satellites. That means they're at a fixed point above the equator. And that's 22,000 miles, give or take a couple of hundred. So they don't move. So they stay over the same position in the Earth's surface. So phone call, router, satellite antenna, satellite down to the ground station where they've got all the big satellite dishes. And then it's going to go through the internet, okay, or the telecommunications network. And that's basically how it operates. Now, it costs you a lot of money, okay? If you want to send a message, it costs you a lot of money, okay? It really does cost you a lot of money. Okay, now there's two main satellite communication systems, okay? The biggest one at the moment, okay, is Inmarsat, International Mobile Satellite Organization, okay? It used to be International Maritime Satellite Organization, but when they started putting the aircraft, they changed their name. For you to send a voice message or a text message through satellite system will cost you between 8 and 10 US dollars per minute. Okay, it's not cheap. The company make deals, so your airline company make deals with the satellite communication. So basically they'll play so much a year. So everyone makes money. That's why now they want people to make satellite calls or use the satellites. And the other one is Iridium, okay? Is Iridium. Iridium is a smaller company, okay? And as I'm aware at the moment, it's just about to happen where this will not be true. They are about to be sending data, okay? They've either just started it or it's just about to start. Where Inmarsat can be voice and data, okay? The one advantage with this is the satellite communications are reasonably reliable, okay? Reasonably reliable, except for two main problems, okay, they have. The first one is, if you're in a thunderstorm, a lightning storm, this signal is very, very weak, okay? So basically, my thunder and lightning, you won't get it, but that's again the same with most communication systems. The biggest disadvantage of satellite systems, remember I said they're orbiting the equator, okay? They're orbiting the equator. And they're commercial companies. So basically, the satellite communications are only looking like for satellite communications where most of the world's population lives. And very few of the world's population live north of 82 degrees or south 82 degrees, okay? So we're actually talking the South Pole and not the north of Norway, north of Russia, north of Canada. There is no satellite coverage for civilian satellite communication systems, okay? So what do we need to know? Okay, satellite communications is data and voice. The satellites are what we call geostationary. They're fixed above the equator. And the big limitation is they don't cover areas of the Earth north of 82 degrees and south of 82 degrees, okay? That's satellite communications. Okay, you all happy with that? Good. Right, the next thing is something called selective calling. Okay, selective calling.
Excuse me.
Yes.
This HF communication, one thing I didn't understand that we cannot physically change the antenna size to ensure optimum propagation, but what we can do is use the antenna coupler into unit to electronically alter the size of the antenna. In this way, we have fixed antenna size made bigger or smaller.
Oh, you're talking about HF?
Yeah.
Yes. So basically, we electronically change the length. It's all done electronically. We don't have a long aerial anymore. Okay, okay, Naveen? It just it artificially does it through electronics. That's all you have to understand. You don't have to understand how it does it. All you need to know is the antenna coupler electronically changes the length of the HF aerial. Naveen?
Yes, thank you.
Okay. The next thing we're going to look at is something called selective calling. Now, I take it most of you've all got cars, yep? What's one of the most annoying things in the world? If you've got a radio and it's not quite on the correct frequency, the correct channel, you get that hissing noise, don't you? Is it really annoying? It is. Or if you're not on the channel, you haven't selected a radio channel at all, you just get that constant hiss, don't you? Yeah. And within 5, 10, 15 seconds, you've had enough of that and you turn it. It's so annoying. Now, remember what I said. There's certain frequencies the pilot will need to listen to. One of them we said was the international distress frequency, 121.5 megahertz. But also, he might want to listen to the frequency for his airline operations to tell him to do something different. He'll have to listen to some air traffic control frequencies that he's been told to listen to. So if I'm not transmitting, and especially on HF, you get this, that hiss. Okay. Can you imagine flying across the Atlantic 5.5 hours listening to that hiss, you go mad. So they developed this thing called selective calling, cell cal. And what it allows the pilot to do, okay, is in the system, he can pre-select certain frequencies that he wants to be able to listen to at all times. Or, to put it another way, he wants to know when the people are transmitting on those frequencies. He doesn't want to sit there and listen to that hiss until someone sends a message. So selective calling allows the pilot to select frequencies and systems that he wants to listen to, okay, or when those frequencies transmit. So let's look at the basic system, okay? We'll look at the basic system. This looks like an HF, okay? Selective calling, we'll look at it. It can do HF, VHF, satellite communications. It can look at the phones inside the aircraft. It can look at certain radio navigation aids. We'll look at that in a minute. But let's just look at this basic system. So there we go. There's my HF control unit. And it could be the exact same for VHF as well. Doesn't matter. So HF, transmitter, receiver, antenna, coupler, aerial. So now once I've selected the frequency, here we go. So my radio signal comes in. We've got the right frequency because the antenna coupler has artificially changed the length of the radio. It comes to here, into the transmitter receiver. It can go two ways, okay? It can go to something called the audio integration system. Okay, audio integration system. That's basically your comms selector box, is what another word to call it. But look, so at the moment, nothing goes there. Let's look at it now goes here. It goes something through a cell cal decoder. Okay, it goes through a cell cal decoder. And what that cell cal decoder is looking for, okay, is a message on the correct frequency, but with the correct aircraft code. Okay, so C, G, B, Z. It's looking for a 4-letter code. Okay, and if the message is not started with this 4-letter code, it doesn't allow it to go through to this what's called a cell cal enunciator. We'll talk about that in a second. And it doesn't allow it to go through to the pilot's headset. Okay, doesn't allow it to go through. I mean, the pilot can take this system out if he wants, so he can go direct. That's why it's got that audio there. It can ignore it straight away. They can ignore it if he wants. But they tend to use the cell cal system because they're only listening for specific frequencies. So like international distress frequency, your airline operations, certain air traffic controllers. So imagine now, okay, gentlemen, I have 3 Air Dubai aircraft flying to Kathmandu. One's leaving, one's arriving, and one's flying past Nepal. If the airline operations want to talk to it, the airline operation has one frequency. But if my airline operation wants to tell one aircraft that when they land, they have to get engineering advice on a vibration. Does the other two aircraft need to know that? No, they don't. So now your airline operations know this 4-letter code. And this 4-letter code is given as part of the aircraft flight plan. So where would you find the 4-letter code to operate selective calling? It will be in the aircraft's flight plan. So now when your aircraft gets the correct 4-letter code, so once we get the 4-letter code, it now allows out the message, okay? It now allows out the message. And on the cell cal annunciator, there's lots of little lights. Every system, every communication system has a little light, LED or a normal filament. And when it comes through, when it gets the right code, it lights up. And the pilot now knows what system, VHF, HF, satellite communication that someone wants to talk to him on. He then selects that system and he can talk to the airline operations. So that's how it works. So your radio system works exactly the same. It's only this cell cal addition. And it's all down to this cell cal decoder. Okay. And it's waiting for a 4-letter code. And once it gets the correct code, a little light comes up on the cell cal annunciator. So let's have a look at this cell cal annunciator. There you go. There's cell cal HHH, 4-letter code. You can see here, right at the top, we've got comms 1, 2, and 3. Well, I know that's actually a VHF. It says comms, that's VHF. So he's got 3 VHF systems, 2 HF systems, and a satellite communication system. He's also looking for certain radio navigation beacons. Yep. He can actually get here, look, the cabin, the old interphone from the outside for you in the ground to talk, where you would tow the aircraft, the old jack. And here, look, the 4-letter cell cal code. Okay, the 4-letter cell cal code. Without it, unless the message coming to that aircraft has the correct 4-letter code, the system, okay, the system doesn't allow the message through. So now the pilot can sit there with his headset on and he doesn't have to listen to communications between other aircraft and their op system. It doesn't have to listen to that hiss. And it's all down to this cell cal decoder waiting for the 4-letter code. Yep, 4-letter code. Now, okay, so here's the next thing we're looking at is it is a 4-letter code. So basically the cell cal requires a 4-letter code. Another bit of information for you to have is, believe it or not, if I've got 4 letters of the alphabet, That allows 10,920 different combinations. Okay, 10,920 combinations. I'm going to come back to that in a second. And it says it can be used on HF, VHF, and satellite communications. Now, gentlemen, how many aircraft were flying in the world at any one time? Less than 10,000 aircraft or more than 10,000 aircraft? What would you say? Who says more than 10,000 aircraft? Put your hand up. Yeah, thank you very much. You put your hands down now, please. And who says less than 2,000 aircraft, 10,000 aircraft at any one time? Yeah, there is at any one time, there is approximately about 10,000 aircraft in the air. That was pre-COVID, okay, pre-COVID. So, think about it now. If I've got over 10,000 aircraft in the world flying, that means more than one aircraft is going to have the same 4-letter code. But how we get around that, okay, is, if I remember rightly, it's ICAO, okay, what they'll actually do, forget the whole world. There's sort of Europe, there's North America, there's South America, there's Africa, bits of Asia, and you've got Australia down there. What they actually do is, okay, what they do is they give each region a certain number of codes, okay? So I would give the codes for VHF, for like aircraft that's going to fly around Europe, okay? So I'll give Europe so many codes. But would I give the same codes to aircraft that might be flying in North America or West Asia? No. So I'd give VHF codes. I might give the same VHF. Let's say I give 1,000 to, let's say, 4,000 codes. So to Europe, and I would probably give 1,000 to 4,000 codes to South America. Yep. So give specific cell-cal codes. So I might give the same code. So I might give 5,000 to, let's say, 7,000 North America for VHF, and I'll give 5,000 to 7,000 in Africa. So those aircraft that are only going to fly around Africa, North America, they're never, ever, ever those come in range of VHF. And I would actually select certain aircraft, okay, that were going to be flying from, let's say, London to Australia. I'd give aircraft that are actually going to be flying intercontinental, they would get certain codes so they could operate all around the world. Okay, so cell-cal uses a unique combination of 4-letter codes, which gives us 10,920 different combinations. And as it says in your notes, duplicate codes are usually assigned to aircraft in widely separate airline areas of the world. Okay, and usually don't have the same HF frequency assignment. Okay, so how do we ensure that no two airlines have the same cell-cal code? Is we make sure that the codes are given to regions that are quite wide apart, like Europe and Australia, North America, Africa, South America, Asia. So there's no way that the communications can mix. Okay, so you're happy on cell cal code? There's not a lot really to do. Why we have it? Okay, so it allows the pilots to listen to specific information that is destined for their aircraft. How do we do that? Each message is preceded by a 4-letter code, and that 4-letter code is included in the airline flight plan. Okay, there's 10,920 codes. How do we make sure that no two codes are used in the same area? We make sure that codes, the same letter codes, are in areas far apart from each other. They're in areas that are far apart from each other. Yes. Yes.
This we cannot duplicate this HF code, right?
You can, okay?
Is
You
it
can, but remember what I said is, if it's regionalised. Remember, how many aircraft fly into Continental? Of all the 10,000 aircraft in air at one time, how many are flying from London to Australia, Australia to Africa, Africa to North America? Not as many. But what we can do is, even if I've got an aircraft flying from, okay, let's say I've got an aircraft flying from London. And let's say I give it an HF code of 27 megahertz. Yeah. So we've got one aircraft is flying from London to Australia. And let's say that this aircraft, with all its VHF codes, is CCDF. I might have an aircraft flying here in South America, and it's got a code of CCDF. Does it matter about cell cal codes for VHF? TR? Does it matter?
no?
No, because it's only 250 miles. So what I would do for this code here, so this airline, its HF, this aircraft, its HF frequency might be 23 megahertz. So it's still the same code, but that aircraft for its HF will be around 23 megahertz. This aircraft, the same code, but its HF would be 27 megahertz. So they wouldn't be given the same HF frequency for that code.
It's due to the range of HF is very high, though it can be contradict, right?
Yeah, exactly. Because remember, HF is worldwide.
Yes.
So even if I've got one aircraft in Europe and one aircraft in South America, both with the same cell cal code, VHF, it doesn't matter. It's only got a range of 250 miles.
Yeah.
HF, it does. That's why the aircraft in Europe would not have the same frequency for HF as the one in South America. So that's why we would never get a crossover. Okay? Because those aircraft would be allocated different HF frequencies. Okay, does that make sense? Yeah.
SATCOM, guys.
Say again?
Same in the case of SATCOM as well.
SATCOM is a completely different system. Okay, SATCOM is a completely different system. Okay, don't worry about how it does it. Okay, it's just like when you pick up a telephone, it gets to you. Okay, there will be a 4-letter code sent down, okay? But remember, okay, I've asked the question. Remember I said that the satellites are over the equator. So if I've got one satellite is covering that area, okay, it'll be a different satellite covering that area, TR. Yep. So each satellite knows where its information is going to be sent. Okay, I'll just leave it at that. I'm not going to make it any more complicated. Yep, but it's still, the message, the satellite communication message will still have CCDF for that particular aircraft. It will still proceed with that. How it get there is slightly different, just accept that the satellite communication, its code will still be the same for that aircraft, whether it's satellite communications, HF or VHF. Okay, the pilot just has to set up the frequencies that he wants. Yeah, does that? You happy with that?
Yes, and thank you. Got
Okay,
it.
no problem. Okay. Next thing we're going to look at is your audio integrating system. Basically, years ago, you would have had, if you go back to that cell cow, this aircraft has three comms, which is 3 VHF radios, 2 HF radios, and they go, look, I've got all these navigational aids, and each one of those, okay, each one of those used to have its own control box. Yeah, used to have its own control box. So you had lots of boxes, a lot of selector boxes in the cockpit. Now we have something called the audio integrating system. Okay, and literally all it does is you have a rotary switch and you turn it to comms 1, comms 2, comms 3, HF1, HF2. And you can also select the navigation aids you want to listen to. So basically, rather than having a lot of boxes, we just have one box. So now the pilot will have one box, the co-pilot will have one box, and it will enable him, the captain or the first officer, to select which radio systems he wants to list via the VH1, VHF2, VHF3, HF1, HF2, satellite communications. Then all the radio navigation systems we're going to talk about later on. He can decide which ones he's going to listen to. Also, all your warning noises, the 2-tone, the 1-tone, the bells for the fire extinguisher, for a fire warning. My cell cow, okay, giving the beep they've got there. The passenger address and talking to the rear cabin crew. I can do it through one box, and all I've got to do is select what system I want to do or talk with, and it automatically selects what we want. So now, rather than having lots and lots of individual control boxes for every radio and every navigation aid, we now only got one system, okay, one that actually allows us to communicate on all our audio and radio systems. Now, as I've said now, on that there, you look how many systems, okay, look how many systems I've got on there. But in this system, there's an interlock, okay? So when I'm transmitting on one, so I might have a navigation aid selected. I'm definitely going to have my warning tones, but let's say I'm listening to my navigation aids, ADF, VOR, ILS, and I then transmit. This is the active one, and what will happen is I don't want to hear my radio beacons going beep, 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 beep when I'm talking on the radio. So as soon as I talk on the radio, the audio from my navigation aids stops transmitting. Okay, so basically the audio integrating system allows me to talk on one thing at a time. So whatever the pilot has selected that he wants to transmit on now, the rest of them he doesn't hear. Okay, so reality is, what is the purpose of an audio integrating system? To basically provide one box to control all my radio navigation and audio systems. And the one thing you might be asked is, what happens when he's listening to one but transmits on the other? When he's actively transmitting, there's an interlock, so he can't hear what the other system is saying. Okay, he won't hear what the other system is, what noise the other system is giving.
And
yes.
so what sort of things categorize their priority? Which going to be bypassed, or which one we want?
Right, we don't normally go into it, but let's think about it. Of all these things, which do you think would have the highest priority?
Obviously, it's navigation, or maybe warning first.
Yeah, of course. If he gets the old bell for the fire warning, the old ring of a bell.
Yeah.
Even if he's transmitting, does he want to hear that? He wants to know the fire, or he's got an emergency. Some of the systems have gone off. So yes, he would have a priority. We remember, this is the basic system, but you are right, there would be a priority. Okay. But you can see here, normally it'd be radio. If he's talking to someone, the rest of these won't come up. But in reality, you are right. If this goes off, he will hear it. Okay, so you are right, but we're talking about the basic system. So as far as we're concerned, for the basic avionics system, there's an interlock that stops him hearing what everything else says. And it's true. If he's talking on the radio, he doesn't want to hear his navigation going beep, 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 beep. Is he interested in the cell call at that moment, giving him a ping to say he's got a message? No. Does he care what the cabin crew are saying in the back when he's on the radio talking to air traffic control? No, he's not. But in reality, you are correct that this would always come through. Okay? But for the basic course, what we're saying is there's an interlock. So when the pilot is transmitting, he doesn't hear anything else. Okay? But you are right what you've just said.
Thank you.
So next thing we're going to look at is something called ACARS, Aircraft Communication Addressing and Reporting System. This is text messaging for aircraft. Now I don't know how old a lot of you people are, okay, how old you are, but are any of you old enough to have an old-fashioned Nokia 3310 mobile phone? Come on, somebody must be. Is anyone old enough for a Nokia phone?
Yes, I have. I used to have.
Who's that?
It's me.
I can't see. Who's that? Prakesh?
Yes, yes.
Yeah. This system is based on the old Nokia 3310 text system. Okay, it's based on this. And if you remember, those who can remember doing a text message in the early days, the length of the message was 220 characters, and then you had to start a next text message. And that cost you money. Okay, so aircars is text messaging for aircraft. Okay. Now, let's look at the system. Okay. Again, aircars. The first thing is it can use VHF and satellite communications. Okay. It can transmit on VHF and satellite comms. So reality is, if I'm flying over, let's say, a populated area of the world like Europe, I can use the VHF system because it's cheaper. If I'm flying over the Atlantic, the Pacific, the Indian Ocean, I can send my text message by satellite communications. Now, I want to talk about something just to understand how this system, what else this system can do. So what we can do, imagine you're fly Dubai, okay? What airlines do you work for in Nepal? Anyone? I can't hear what you're saying, Naveen.
Yeti, Buddha.
Nepal Airlines.
Nepal Airlines, yeah.
Nepal Airlines.
Okay, Nepal Airlines. You've all seen Fly Dubai coming into Kathmandu, haven't you? It's a low-cost airline.
Yes.
And of course, they want you to buy their food. You don't get, all you do is get a seat. You don't get any drink. You don't get any peanuts. You don't get any crisps. You don't get a meal. Before we had this aircar system, if the cabin crew wanted to order more gin and tonic or peanuts or meals, they would have to talk to the pilot, and the pilot would have to talk on VHF, HF, or satellite communications to order more peanuts, etc. Now, the cabin crew, by the old flight attendants panel, can put in a message to order peanuts to be at the next airport when they arrive. So it takes a bit of work away from the pilots. The next thing is, gentlemen, I don't know if anyone can contact Suresh Sharma. He keeps trying to get in, and I'm admitting him, but unfortunately, it's not allowing him in. Okay, I don't know why. Oh, he's just got in, right? Okay. So that's what we can do. We can send text messages. I want some more peanuts when we arrive at Delhi. Easy. But the one advantage this system is got, if you look here, it can send data from your aircraft systems. It can send data from your aircraft systems. It can monitor. It can send information on the systems in your aircraft, how good they're doing. Your engine information. Now, certain airlines, okay, some airlines have bought their engines from the engine manufacturer, and some airlines lease or rent their engines from the engine manufacturer. I'm going to give you two examples. I have a friend of mine who works for Rolls-Royce, and he sits in their operations centre in Derby in the UK, and he monitors information. And airlines like British Airways, they lease their engines from Rolls-Royce. And part of the contract is once every 3 minutes, they have to download data on the Rolls-Royce engines that they own or they lease. And with this data, you can get your N1, you can get any vibrations, you get any over temps, you get all that information. It also gives the position and the time relative to GMT. So it gives the aircraft a position. Another airline, Air Malaysia, they bought their engines from Rolls-Royce, and they only have to send data on the engines once every hour. Have you all heard of Air Malaysia flight MH370? The airline the aircraft that disappeared. Yeah. And if you've ever read any of the papers or seen any of the documentaries on television, they knew it continued for flying for 5 hours because the aircraft system automatically sent data on their engines to Rolls-Royce. And that data had the position, so they knew it went up, turned right left, and came back down into the Indian Ocean. And then they lost it. So they knew where it was. But now you're looking at nearly 700 nautical miles radius where that aircraft went down. That is a lot of sea. And what's looking at, the regulations about to change, the aircraft will have to update their information once every 3 minutes. So the aircraft system, yes, we can send text messages saying, I want some more peanuts. But more importantly for us, as aircraft engineers, the data comes from our aircraft systems, okay? And it comes to this unit, it's called a data acquisition unit, okay? The data acquisition unit takes all the information from the aircraft systems and puts it into a format that the ACARs can send out via satellite or VHF, okay? So where does the information from the ACAR system collected? It's collected by something called the data acquisition unit, okay? It goes to something called the data acquisition unit. The data acquisition unit, we'll look at this later on, that also provides information for your flight data recorder. Next thing, if I get a message in from the ACAR system, okay, I get a message from the ACAR system, it comes into the ACAR system. The first thing is, we get a little light on the centre of the aircraft's instrument panel, little light saying you've got an ACARS message. And this ACARS message can be displayed in two ways. So the multifunction display in the centre console of your aircraft in the cockpit, you can come up here with a text message. But you can also print it out, okay? You can also print it out. And if you look here, from my multifunction control and display unit, there's a connection to my flight management system. Okay, my flight management system. And gentlemen, this is where the computers have taken over the world. Your airline operating, your airline operation system, your airline operations can actually now send an ACARS message through VHF or satellite communication to change the flight plan of the aircraft. So it can come in and straight into the flight management system, and the flight plan of the aircraft will change. I find that scary, gentlemen. I really do. That we can change the aircraft navigation, its flight plan, by a text message. Okay, so on this screen here, be aware of where aircraft information goes before it's sent out by the ACARS system. It's sent out by the data acquisition unit. So the data acquisition unit collects the data before it's sent out by the ACARS system. What ways can the ACARS system display a message? We can display it on the multifunction control, or we can send it, or we can print it out by the printer in the cockpit if your airline has it. Not all the airlines have it, quite a few do. And I can also send an ACARS message to change the flight plan of my aircraft. Okay, I can change the flight plan of my message.
Hello, Ian.
Yes.
Can you please repeat that portion again, changing the flight plan?
Yeah. We don't mention it too much. We just talk about the airline's operations center. It can actually do things. But if you can see here, I can yes.
Can we change the flight plan from the ground?
Yes, they can. Oh, yes. I find that scary. But yes, they can. They can now change, as you can see here, the flight management system. That's your aircraft's navigator. That's your aircraft's computer that does the navigation. I can print it out. I can change the flight plan of my aircraft, and I find that scary. Yep. But that's it. So let's look at the makeup of the message. Okay. The first thing is, a ACARS message is, 220 characters long. If I have more than one message, we call it a multi-block message. Okay, so gentlemen, let's look at how we can ask a question on this. So if I have a ACARS message which is 890 characters, how many messages are going to be in this multi-block? Well, let's do a quick bit of maths. 220. Yeah, 220 into that. So 4 times that gives me 880 plus 10. So it's 4 messages plus 10 has got to be another message. So my total number is 5 messages. Okay, it's just another way to ask about multi-block messages. Okay. So it's 220 characters long. Any more than that goes into a multi-block message. Right, gentlemen, we're going to go for a quick 10-minute break. Okay. I'm going to go to the toilet, grab a cup of coffee, and I'll be right back in 10 minutes. Same with you, get up, get a stretch, get out your seat. Okay, see you in 10 minutes. Hello, gentlemen. Right, so that's just really done the communication side of our avionics, okay? We're now going to look at our radio navigation aids, okay? We're going to look at the radio navigation aids. And they allow the pilots to fly in bad weather and at night where they can't see the ground, they can't use a map, or they're very high up in the air and they can't see the ground. Radio navigation actually started in the 1920s. So actually not long after flight started, okay? And it was allowed to allow aircraft to fly from one side of the United States to the other. So they brought up this type of radio navigation, okay? And that's what we're going to look at, we'll start looking at this afternoon. And the very first thing is automatic direction finding, otherwise known as ADF, okay? Otherwise known as ADF. I'm going to come back to this slide in a minute, okay? And we'll look at how the system works first. Right. We're going to look at basic electrics to start with. Here's my radio wave, okay? It's an AC. And as I said this morning, okay, the amplitude, yeah, so the amplitude of the waveform, okay, we can actually say is the voltage or power, okay, but we'll call it voltage at the moment. Now, we know from basic electrics, if an AC waveform, okay, an AC waveform cuts a conductor, it produces an EMF or a voltage. So you can see now that this waveform, when it cuts a conductor, will produce a waveform. Now we're going to look at the construction. Now we're going to look at the construction of an ADF system, okay? It's made up of two aerials, okay? The first aerial is what we've got there, it's called a loop. And the other one's called a dipole, okay? So the loop aerial is the one at the top. The dipole aerial is just a single aerial. So like a whip aerial, single aerial, just like your car aerial for your radio. Now, let's look at this aerial. So now I have a waveform cutting one side of the aerial, producing an EMF, and other side of the waveform cutting the aerial. So basically, here's my transmitter. Okay, there's my transmitter. And it's sending out that AC waveform. So if I've got this loop antenna side on, okay, so there's my loop antenna. So the camera is my transmitter. If I turn the loop aerial side on, at one point the voltage is hitting here on that side, but it's hitting down here at that side. And what's going to happen is there's going to be two voltages induced, okay, two voltages. That's going to produce an EMF, okay. That'll produce what's called a potential difference, an EMF, and a current will flow, okay? a current will flow. And that'll allow the system to operate, okay? That will allow the system to operate, okay? And when it operates, it will do two things. It creates a magnetic field in here, and it also allows us some Morse code, dot dash, dot dash, dot dash, to come through. Yep. That's the loop aerial when it's side on. Now, if I bring the loop aerial and I face both sides to the transmitter, both sides, I can now see that the waveform is going to hit at the same place. Okay? It's going to hit at the same place. And it produces no EMF. There's no potential difference, and therefore there's no current in the loop. Okay? And we get a null point. So now what we get when we're not directly on it, we get this. Okay? I can get what's called a magnetic field. Okay? And it has two null points. So when my loop aerial is facing you, I get a null point. But look here, when I turn round, my loop aerial is also directly at the transmitter. So when I get no EMF induced into the loop aerial, it means I'm actually going directly to the beacon or directly away. Okay? That's not too bad. So I either know the beacon is directly there and I can navigate to it, or it's that way. I have a choice which way to fly. If I'm short of fuel, I have problems. So this is where this dipole aerial comes in, okay? This dipole aerial. This also puts up a EMF, and it also produces a current, just like here. So this is my loop. And this is my what we call dipole, the single aerial. And that is the magnetic field, okay, that is produced by both these aerials. But now when I put them together, we get this, it calls your notes a cardioid shape, okay? A cardioid shape, a heart shape. Okay. And what we're looking at now is this one bit here. So now, rather than having two null points, we have one null point. And how the system works, gentlemen, okay? In my ADF control unit, I will type in the frequency of this beacon, okay? And we call these beacons non-directional beacon. And it sends out a Morse code signal. So I tune in to a beacon, and the camera is the beacon, but I'm actually pointing away. So now I'm going to get an EMF. So I'm going to get a current flow. The system is detecting the beacon, but it's not directly at the beacon. So what happens is I'm flying this way, but I really want to be going this way. And what we'll get in the ADF system, we'll get a Morse code. Beep, 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 beep. And as soon as I turn towards the beacon, it will go beep, 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 beep. And as soon as I'm directly in line with the beacon, we've actually got this null point. Yep. So the pilot won't hear anything in his antenna. Okay? He won't hear anything in his antenna. So that's the first thing. So let's go back to this here, okay? In your aircraft, you can have two, okay, indicators. There's RBI, remote bearing indicator, and RMI, radio magnetic indicator, okay? One of them will tell you the direction to the beacon, and one of them will tell you your angle relative to that beacon related to north, okay? So my relative bearing, okay, my RBI, okay, will tell me what angle, okay, the RBI will tell me what angle I need to be to fly to the beacon. The relative magnetic, sorry, the radio magnetic indicator will tell you the angle relative to magnetic north, okay? It's just two ways to give that information. Right, so what do we need to know so far? We need to know the construction of an ADF system. It relies on beacons, okay, and they're called NDBs, okay, and that stands for non-directional beacon. It's just a radio signal. It fires out 360 degrees. That's on the ground. In the aircraft, we have the ADF aerial, and the ADF aerial is made up of two aerials, a loop aerial and a dipole aerial, straight up and down. A voltage will be induced into the loop unless it's directly pointing, both sides of the loop are directly pointing to the non-directional beacon. If I'm pointing at the non-directional beacon, I can have two null positions because the beacon could be that way or that way. But this is where the dipole comes in, okay? When the dipole is behind the loop aerial, we get that cardioid. So basically, wherever the null point is where that is the angle or where the aircraft is directly in line with the beacon, okay? Directly in line with the beacon. And that shape here is called a cardioid shape, heart shape, cardial heart. Okay. So when we've only got one null point in that cardioid, that is the direction to the beacon. Now, as I said, he gets an audio. The voltage produced by this is what turns the indicator. But also, it also produces, it picks up the audio sound. And the audio sound is Morse code. Dash, dot, dash, dot. Okay. And the beacon, the non-directional beacon, the NDB, produces, okay, a Morse code signal of 2 to 3 letters, 7 times per minute. Okay, so the NDB transmits a Morse code signal of 2 or 3 letters up to 7 times per minute. And that's how the pilots know they're selected to the correct beacon. Now, you won't be able to see that, but this is an aviation map. Okay, and on this aviation map, I've got, it's very different, you won't be able to see it, but I've actually got different, I've got all the beacons. And actually, it'll tell me the Morse code signal for that beacon. So I know which one I'm flying to. Okay, so that's one way we can do it. So we're happy with the construction of the ADF. There's 2 aerials, a loop and a dipole. When I'm pointing directly to the beacon, I get this cardioid shape, and the null is pointing directly to the beacon. Okay, and the non-directional beacon is transmitting a radio signal which carries a Morse code of 2 to 3 letters 7 times a minute. Okay, and there's your basic system. There's the control unit. You put in the frequency you want to learn. There's my aerial. We'll get the Morse code on the headset, and there's your remote magnetic indicator, which will point the direction to that beacon. So, gentlemen, it operates over quite a wide range of frequencies, okay? 190 kilohertz to 1.75 megahertz. Again, remember frequencies. It's called a ground station. Okay, the ground station is your non-directional beacon. Again, there is 2 types of non-directional beacon. The ones at the airfield are low powered, okay? Low powered. Again, 20 to 30, maybe 40 watts. So its range isn't that far. But we actually have high powered ones, okay? And again, remember I said about going across the Atlantic, we have a control centre in Scotland and we have a control centre in Canada. Well, they also have an ADF beacon, but they have them of thousands of watts. So it can go hundreds and hundreds of miles into the Atlantic. Okay, hundreds of miles into the Atlantic. Okay, so let's just run over what we need to know on ADF. The beacon, the radio beacon, is called a NDB, non-directional beacon. Operates on the frequency of 190 kilohertz to 175 megahertz. It transmits a Morse code signal of 2 to 3 letters 7 times a minute. Let's look at the aircraft. The ADF system is made up of 2 aerials, a loop aerial and a dipole aerial. When this aircraft is pointing towards the beacon, the magnetic signature around those beacons is a cardioid shape, and the null point is where it's pointing to the beacon itself. So when the aircraft is not directly pointing to the beacon, I will get a Morse code. When I'm in line with the beacon, we're at a null point, nothing, 0. Now this is an older system, okay? It's now been taken over. Used to be a box hanging below the aircraft. It was quite heavy, and it was in the airflow of the aircraft. They've now replaced it with a little aerial, okay, about that size. So it went from a big box like that underneath the aircraft to a little aerial like that. But the principle it works is the same. So remember that. 2 aerials, dipole and loop. When the aircraft is pointing directly to the beacon, we get that cartoid shape with the null point where we do not get any Morse code. The beacon sends out 2 to 3 letters 7 times a minute. Anyone get any questions on ADF? No? Good. The next one we're going to talk about. Yes.
In the last slide, where that nighttime range, the last one, what is that?
Yep. Remember, like HF, it bounces around the ionosphere.
Yeah.
So basically, at night time, the ionosphere goes up. So actually, it can interfere with the range of the ADF. So its range becomes shorter at night than it is in the daytime. You don't have to know how much, okay? But just be aware at night time, the range of the ADF is slightly shorter. Okay, happy on that?
Okay.
Yeah. The next system we're going to look at. Pardon?
Hello. Hello.
Yes,
Yeah.
okay. Yes.
Can you again please shortly explain this, because I am still not clear about this ADF.
Right. The first thing is 2 aerials. Yep.
Okay. 2 areas.
A loop and a dipole.
A loop and a dipole.
Yep. So loops. A dipole aerial is just like the car aerial on the car. It's straight up and down. One straight line. Yep, like the pen. The loop aerial is a loop. And you can see here, if this waveform cuts in 2 different parts of the conductor, you can see the power. Remember I said voltage is the amplitude? So here it's got quite a low voltage. Here it's got quite a high voltage. I've got 2 potential differences. I'm going to get a current flow. Yep.
Okay.
Yep. And when the loop, both sides of the loop are at the beacon, pointing directly, they're both going to have the same voltage induced. There's no potential difference, therefore there is no current flow. Right?
Okay.
Yep. Now look at, here's my loop aerial. And when I am in front of the beacon, so I'm flying towards the beacon, the signal produced on both sides of the loop, here, okay, it produces this signal waveform, okay, this signal round the loop aerial. But you can see now, I have 1 null point and 2 null points. So actually, without the dipole, I could either be heading directly to the beacon or directly away from the beacon. So this is where this dipole comes in. So the field produced by this dipole interacts with this, because these 2 aerials are literally about that far apart. Okay?
Okay.
These interact. So what you've got here is reality is I've got that there, and that there. Okay, so that there's my dipole, and that there is my loop. And now with the aerial behind the loop, I've only now got 1 null point. Yep. So the null point will point towards the transmitter. And that's the basics of the system working. It gets a null point. And with that null point, will be going directly towards the beacon. And that beacon is going to transmit, as I said there, 2 to 3 letters 7 times a minute. And the only time it doesn't pick up, the pilot can't hear that Morse code, is this bit here. Okay, in the loop. So when he's flying, he's flying that direction, but he wants to come to the transmitter here. Okay, so he's flying this direction. It'll get beep, 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 beep. So the aircraft now turns round. Beep, 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 beep. And the closer I get to in line with the beacon, the noise, the strength of the Morse code goes down. So it goes beep, 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 beep. So the Morse code, its level reduces until it gets none when he's in front of the beacon.
Okay.
Okay. Yep.
Okay.
Good.
Okay. And so yeah, this how this work in the in the instrument, is it? This is not important.
What do you mean?
This indicator.
All it's going to tell you is the bearing to the beacon or your angle flying to the beacon. Okay. That's all it's going to. It's going to tell you where you're going to the beacon or your angle relative to the beacon. Okay.
This really RMI.
Pardon?
RMI will show the aircraft's position relative to the beacon.
Yeah, the RMI will give you your angle relative to magnetic north. Okay. Yep.
Okay.
So it gives it relative to magnetic north. The RBI, the relative bearing, if you actually look at the two of them, both will still say west. Okay. One of it gives you directly relative to magnetic north, and the other one will point directly to it. Okay. It still will give you the same angle. But one will point that one will give you the needle to point directly to it, and that's the RBI. And the other will give you the heading, okay? Just give you the actual heading relative to magnetic north. So the RBI, the needle will point directly to the beacon. The RMI gives you the heading relative to magnetic north. But they'll both actually say the same. Okay?
Okay.
Right, so next one we talk about is VOR, okay? VOR, VHF omnidirectional radio range. It's a very good system. It's a very good system. Most of your major airports will have this, okay? And they also tie it in with another system that we'll talk about next. Okay, what we're going to look at is a VOR system. It uses two types of radio system. The first one is VHF, and the other one is UHF, okay? I did say this morning that is basically for communications left to the military, but we said we still use it in some of the navigation aids. And what we're going to do is actually compare the phase difference between the two waveforms, okay? We're going to look at the phase difference between the two waveforms. Now, there's two types of VOR out there. There's conventional VOR and there's Doppler VOR. The only doesn't matter in your aircraft, the aircraft system can detect both. The aircraft system can detect both. All that happens is in conventional VOR, VHF is your reference and UHF is your radial. We'll look at what radial is in a minute. And in Doppler VOR, it becomes UHF. Sorry, not UHF, that's not HF. What am I saying? Rayburn, you're an idiot. Not UHF. And FM. Okay, is your radio. And of course, we know VHF is also known as AM. Now, what the beacon is going to do, it's going to send out, I've got a picture. I've got a picture on this screen. What the beacon is going to do is going to send out two radio signals, one AM, one FM. And it's going, so what's going to happen is, bang. The first thing is it sends out, at the same time it sends out, okay, oops, a reference signal. So basically, it's like me dropping a stone in some water. We get the concentric circles going out. So that's my reference radio wave. The next thing is, at the same time my reference goes out, I send out this radial, okay? And it's going ping, 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 all the way around, 360 degrees. And what the aircraft's VOR system is looking at the phase difference between the two radio waves when it arrives at the aircraft. Okay, when it arrives at the aircraft. So if my aircraft was directly north of the VOR transmitter, the reference, the reference signal would be in phase with the very first one, because they both started at the same time. If I was east of the transmitter, the reference, as you can see here in red, is the same. But now you can see that the radio must have started 90 degrees later. So I have a phase difference of 90 degrees. So my VOR system will know I am 90 degrees or east of the beacon, or the VOR beacon, the VOR transmitter. If I'm directly south, the radio will be 180 degrees difference from the reference. So the aircraft will know it's directly south of the VOR beacon. And if I come to here on the left-hand side, the reference is still the same, it hasn't changed. But now the radio, it started 270 degrees later. So it can tell me I am directly west of the beacon. And it can actually tell you, it can look at the phase difference and go, you're 020, 20 degrees, 240 degrees. So it can tell you your angle to the beacon, okay? It can tell you your angle to the beacon, okay? So that's it. So how does the VOR system work? It sends out an AM and an FM signal, and it compares the phase difference between the two when it actually gets to the aircraft. Okay, it gets to the aircraft. So that's the basics of operation. Okay. The other thing it can actually do, you can actually adjust it, and it can allow you to fly at an angle. Okay, an angle to the bearing, and again that would be displayed on your RMI. Okay, relative magnetic indicator. So basically, it can allow you to fly to and from. Okay, at an angle. The other thing it allows you to do, if you look here in this RMI indicator, let's get a different colour. If you look here, you've got that little 2, okay? What the VOR system in the aircraft allows you to do, okay, is when I select what we call OBS, okay? It's just called the OBS, it's called the Omni Bearing Selector. What you can do is you can dial in, okay? Like for instance there, that is, you see it there, there's 10, 20, 30, 40, 50 degrees, okay? And what this allows you to do is select a bearing to fly to that beacon. So what you can do is you can fly, and the system works out the angle, and you can turn your aircraft to fly at a particular bearing to that beacon, okay? And that's called the OBS, the Omni Bearing Selector, okay? And it just says it allows him to fly to a bearing to that beacon. But also in here, it's got this little to and from, okay? And it tells you, the pilot, that he's flying to the beacon. It's that clever. And if the aircraft was here, this little beacon would come down. You get, if I actually look at it now, there's my, it says 2. And it can also say that, from, FR from. So it can actually tell the pilot if he's the beacon at that angle or flying away from the beacon at that angle. Because you can see here, it could be flying to the beacon or flying away from the beacon at 50 degrees. So it tells him when he's flying to or from. Okay. Same setup as we had there. You've got control unit, transmitter, receiver, headset. Because guess what, gentlemen? The VOR beacon not only sends out directional information, it sends out a Morse code. Guess what, gentlemen? It's 2 to 3 letters. Guess how many times a minute? 7 times a minute. So what I'm going to say to you now, ever asked about a Morse code signal sent on any radio navigation aid, it's always 2 to 3 letters, 7 times a minute. Always remember that, 2 to 3 letters, 7 times a minute. Okay, gents, here comes the data. Okay, in your notes, it will say the frequency is 108 to 177.995 megahertz. Everyone calls it 108 to 118. 108 to 118 megahertz. It's easier to remember. So what's the operating range of VOR? It's 108 to 118 megahertz. It's good up to 250 miles. Okay, it's good to 250 miles. I did also say it gives you the Morse code, 2 to 3 times a minute. So 2 to 3 letters, 7 times a minute. And it's accurate at 250 miles to plus or minus 5 degrees. And the closer you get, the more accurate it becomes. And the last thing is this thing called the cone of confusion. Okay, if you can see, gentlemen, the radio beams go out from the transmitter in a V shape. Okay, so they go out, but also go up in this V shape. So when I'm flying at 30,000 feet, yep, when I'm flying it, you can see here, out where my hand is, I could pick up at 30,000 feet, the VOR beam. But now when I start to move into this V shape, I'm not picking any radio signal up. And what happens in my VOR indicator, my RMI, the needle just goes round looking for a radio signal. It can't pick any up. So it just goes round and round. So we call this area directly above the VOR transmitter the cone of confusion. Okay, we call it the cone of confusion. And that extends at 30,000 feet to 8 miles wide. So 4 miles either side of the beacon. We have what's called the cone of confusion. And that is where the aircraft's VOR system cannot pick up any VOR information. Cannot pick up any VOR information. So let's highlight what we need to know about VOR. It works on 2 radio signals, FM and AM. And the VOR signal is going to detect the phase angle between the reference and the radio, the one that's going round, firing 360 times. It looks at the angle between the two. And the angle, the phase angle between the 2 radio signals, the AM and FM, is the bearing to the beacon. Okay, the bearing to the beacon. But the system is very, very clever, and so is the aircraft system is very, very clever. And what we call the OBS indicator, the Omni Bearing Selector, the pilot can select an angle to fly to that beacon. Okay, doesn't have to fly direct. They can fly along and then turn to fly at the angle to that beacon. What else was I going to mention? Oh yeah, and it can tell them, there's a little triangle that tells the pilot if he's flying to or from. Okay, flying to or from the beacon. Oh yeah, one thing I forgot, gentlemen, on here. Yeah, on the OBS, as I said, it tells you your left or right. You have this bar here, it's what's called the steering bar. Okay. And on here, okay, the steering bar tells the pilot to, if you look at here, to get on that 50-degree angle, it has to fly left. So in my OBS, my Omni Bearing Selector indicator, it can select an angle to fly to that beacon, that VOR beacon. it'll tell him whether he's flying to or away, and the steering bar tells him if he's left or right, has to fly left or right to get to the correct angle to fly to that bearing to the VOR indicator. Remember the information: 108 to 118 megahertz, 250 meters range, Morse code, 2 to 3 letters, 7 times a minute. There's an accuracy of plus or minus 5 degrees, and that accuracy gets better the closer you get to the transmitter. And we have that cone of confusion, which extends 4 miles either side of the beacon at cruising altitude. So it says there 8 miles, and that's where the indicator just goes round and round looking for a signal but won't find it, and that's why it's called the cone of confusion. Anyone got any questions on VOR for me, please? No? Okay, good. Next thing we're going to talk about is ILS, the Instrument Landing System. Most big airports have it. Even some smaller airports have it. And it allows the pilots to basically land when the weather isn't all that good. Okay, and that's what it does. That's its main purpose. But VOR comes in 3 parts. Okay, VOR comes in 3 parts, and we're going to look at what it does, what the 3 parts are, and what they actually tell the pilot. So, there's the purpose. It's a ground system that does 3 things. It tells the pilot, 1, whether he's down the centre line of the runway. The second thing it does, it tells him, is he at the correct approach angle? Okay, and that's usually about 3 degrees. And the third thing is, it can actually tell him how far out from the end of the runway the aircraft is. And we're going to look at these 3 systems. There are 3 separate systems built into this one ILS system. Okay, we're going to look at the 3 different systems that make one big system, ILS, Instrument Landing. So let's look at the first part, and it's called the localizer. And the localizer allows the pilot to line up his aircraft down the centre line of the runway. Now, you've probably seen it. Has anyone ever been to the end of the runway at Kathmandu? You've got it looks like a big red and white fence right at the end of the runway. Anyone seen that? Anyone?
Yes, yes.
Yeah, that's the localizer. That is the localizer aerial. And there should be one at each end of the runway. Okay, because you can come in that side and you can come in that side. The localizer, okay, is VHF, okay? So when the pilot comes into Kathmandu, my books. What you can actually do, you can either look at his aviation map, or you can look at the books, and it will give him the frequency for the localizer at that airfield. And remember, he's going to have 2 frequencies. One for one end of the runway, one for the other. And we'll look at frequencies in a minute. So the localizer is a VHF radio system, and it allows the pilot to line up with the center line of the runway. How does he know he's down the center line? So what we have on the VHF, we have our carrier wave, okay? And that's what the pilot tunes in the ILS system. So we have a carrier wave. Yep, carrier wave. But on the left-hand side of that carrier wave, we put a modulated frequency of 150 hertz. On the right-hand side of the runway, we have a modulated frequency of 90 hertz. So when I'm approaching the center line of the runway, so my aircraft is approaching the center line of the runway, he will get equal amounts of 150 hertz and 90 hertz. And the indicator, I've got an indicator somewhere. All right. The indicator will indicate straight down. I'll have a vertical bar and it will be straight down the center of the indicator. If I move to the right-hand side, so I'm right of the center line, I'm going to pick up more 150 hertz than 90 hertz. And it will cause the indicator to move to the right of the runway. Okay. And if I was to left, it'd pick up more 90 hertz, so it'd tell the system it was left. Okay. So that's how the system works. Okay. So the first thing you got to remember, what does the localizer do? It allows the pilot to line up with the center line of the runway. It is a VHF system. So the localizer is VHF. How does the pilot know whether he's left or he's down the center line of the runway? He will get equal amounts of the 90 hertz and the 150 hertz modulation. And if he's too right, he gets more of one and less. So remember the two frequencies. You don't have to remember it's left and right. Just imagine, okay, you do need to know the modulated frequencies, and you do need to know that the ILS part, the localizer, is VHF. Right? So that's what you need to remember for localizer. The second part is glide slope, okay? And glide slope is a UHF frequency, okay? So the carrier wave is a UHF frequency. But just like the localizer, it now has a modulation of 90 and 150. If he gets more 90, it means he's above the correct glide path, the correct approach to the airfield. And again, that's usually about 3 degrees. If it gets a lot more 150, it tells him he's below the glide path. Okay, is below the glide path. Oh. Okay, somebody's got their microphone giving feedback. Now, what I'm going to say to you, I haven't mentioned, apart from it's a UHF, I haven't mentioned selecting a frequency. Okay, I haven't mentioned selecting a frequency because, gentlemen, it's the ILS system I know we said there's 3 parts to it, but it's the ILS system. So as soon as the pilot tunes in the localizer frequency, so as soon as the pilot tunes okay, as soon as he tunes in the localizer frequency, your ILS system automatically pairs it with a glide slope principle, a glide slope frequency. There is 40 ILS frequencies in the world. There is only 40 ILS frequencies frequencies. Each one is paired with a glide slope frequency. So the ILS system in your aircraft is only going to operate 40 pairs of frequencies. So if I tune in a localizer frequency, let's say I tune in channel 1 of the localizer frequency, whatever the localizer frequency, it will be paired up with the same glide slope frequency no matter where we are in the world. So we only need 4. So you have to remember that. Why don't I need to tune in the glide slope? Because it's always automatically paired with a frequency on the localizer. Okay, so we only ever tune in for ILS, the localizer frequency. Okay, happy now? You all happy? Yes.
It's a two-way or one-way, like localizer itself automatically tune the glide slope?
Yes.
If we tune the glide slope, it will automatically tune the localizer?
Yes, it is. So no, you only tune in the localizer frequency. It's automatically paired with a glide slope frequency. So no matter where you are in the world, you choose channel 1. Okay, let's say channel 1 in is for one of its runways. Okay, it's a channel 1 ILS, and let's say that is 123.5 in the VHF. Okay, automatically paired with 0.7. So no matter where you go in the world, so Heathrow runway number 1 or left right runway, it's one of its ILS channels is channel 1. Its localizer will be 1.3.25. That's all you tune in. And it's automatically paired with 260.7. Those two frequencies will be allocated together. Okay, does that answer your question, Tia?
Okay.
Good.
Okay.
So there's only 40 frequencies in the world, and we only ever tune in to the localizer frequency. And each one of those frequencies has a modulation of 90 Hertz, and 150 hertz. This tells you whether you're left or right of the localizer or above or below the glide slope. Okay. Meters wide. And what happens is the aircraft approaches down the localizer on the glide path throughout the world. Okay, they're the exact same throughout the world. 400, 1.3 and 3 kilohertz. Don't worry about memorizing frequencies or Morse code for these. Okay, you don't have to worry about that. But what happens is the aircraft approaches, that beam hits the bottom of the aircraft. You have a little what's called a marker area or a marker antenna. And as soon as the outer beacon, the 400 hertz, hits that, the system detects 400 hertz and it puts a blue light in the ILS system. Now this might be on the, for glass cockpit, it'll be a little blue light in the primary flying display. As it gets closer to the end of the runway, it flies over the middle marker, which is an amber or orange light. Okay, amber or orange light. And as it continues, it then flies over the inner marker beacon, and that will produce a white light. Okay, what you could be asked, gentlemen, is what is the order of the lights in the ILS system? Okay, and the order is blue, orange, white. Okay, or ball. Okay, if I change that to orange, okay, because it's amber, we get the word bow. And that's how I've always remembered it, gentlemen. Blue, orange, white. Amber and orange, you can agree, all look the same. Would you agree that that can be classified as amber or orange? So I've always known the order of the ILS lights as blue by the word bow, as in tie a bow on your shoelaces or a bow tie. Blue, orange, white. So you are possible. You need to know the order of the lights, the marker lights as they approach the aircraft. Aircraft approaches the runway, and that is blue, orange, white. Okay, you have to remember the order of the systems. Okay, you have to remember the order of the systems. Hello?
What about the frequency?
What's that? Don't worry about the frequency of the marker beacons. Just remember the order of the lights. Okay, that frequency, these frequencies don't change throughout the world. Okay.
Okay.
Right. Next thing we need to think about is as you can see there, there's your ILS display. You've got the beacons. So you've got two lines. The vertical line tells you where you're left or right of the glide slope. The horizontal line is telling you whether you're above and below the glide slope. And then you've got your three marker lights. Okay, you've got your three marker lights. And just remember, there is also a Morse code as it flies over the marker beacons. Don't worry too much about the frequency or the the letters. Okay. Now.
Hello, Ian.
Yes. Yes.
Hello. Can you go back to the indicator? How the indicator will show the whether it is above or below?
Hold on, let me get the color. So this line here is a bar, okay?
Okay.
Right? This bar here,
Okay.
that will tell me if it moves over here, it will tell me I am left of the localizer. If it was over here, it would tell me I was right of the center line of the runway. Happy with that?
Okay.
Right? And this line here is my glide slope. So if it's up here, it tells me I'm above the glide slope. And if it was down there, it would tell me I was below the glide slope. Yep.
Okay.
That answer your question.
Okay. Thank you, Ian. Yes.
Yep. That's so basically it'll tell if I'm below, I'm getting more of one modulated frequency. If I'm in the center line of the localizer or the center line of the glide slope, it means it's getting equal amounts of the 90 degrees and the 150. Okay, so please remember that. How does it know if it's flying down the center line of the runway? It will get equal amounts of 90 degrees and 90 hertz and 150 signals. Okay. Right, so we're going to go through. Yeah, so localizer center line. It's a VHF system, and it has a 90 degrees modulation on one side and a 150 on the other. And if the ILS system picks up both equal amounts, it's center line. Glide slope is a UHF system, and that tells you where I'm above or below the correct glide angle, the correct approach angle, which is 3 degrees. And again, it has a modulation of 90 and 150. And if it get equal amount of modulation, it must be on the correct glide angle. And the third part is the marker beacons. It sends the radio wave up and it will put a light on the cockpit. The outer is blue, the middle is orange or amber, and the inner is white. So blue, orange, white. As I said, there is 40 ILS channels in the world, but we only ever tune to the localizer frequency because the glide slope is automatically paired with a localizer frequency. Yep. The localizer can go out to 40, sorry, the localizer can go out to 25 miles. The glide slope is usually picked up at 10 miles. Okay. Guess what? The localizer also sends out a Morse code of, guess what? 2 to 3 letters, 7 times a minute. Okay. So that's the information you need to know. So there's only 40 channels and we only tune in to the localizer. Localizer has a range of 25 nautical miles and glide slope has a range of 10 nautical miles. And the localizer, remember that it's the localizer, sends out a Morse code signal of 2 to 3 letters, 7 times a minute. Okay, 2 to 3, 7 times a minute. Okay, gentlemen. Next thing we're going to look at is global or GNS, satellite navigation. Okay, it's called Global Navigation System. How it works, okay? There's two main systems. Well, there's actually three. Well, there's two main systems. There's an American system called Navstar. That's the one we all use, okay? That's the one we all use, and I've got mine here. And it uses satellites. There's a Russian one, it's called GLONASS. It's only ever used by Russian aircraft, okay? And I don't know a great deal about it. The principles is, I believe, the same. And you've got a Chinese one, and you've got a European one, okay, called, what's it called? Not Marco Polo. Yeah, Marco Polo. It doesn't work yet, okay? It doesn't fully work. So what the principle is, okay? The principle is time, speed, and distance, okay? Time, speed, and distance. And what we're going to look at is how this system works. Now, each satellite has, it's a word we call an almanac. Basically, it has a lot of data. And in this data, the satellite knows where it was, where it is, and where it's going to be at a very accurate time, because it contains atomic clocks. This timing has to be very, very accurate. The clocks are accurate to about 1 second in a million years. How the system works, okay? I've got one here. My little satellite, my GPS receiver, is going to pick up this satellite information. It knows the satellites, okay? And up there is 21 active satellites at any one time and 3 in standby mode. There is more than 24 satellites up there. Some are shut down, some are getting repaired, some are completely broken. But there's 21 active satellites in the GPS system, and 3 are in standby. Okay. The system there's 6 orbits. Okay, we'll look at that in a minute. There's 6 orbits. But what this system allows us to do, okay, if I'm only tracking one satellite, when I'm looking at the beam, you can see here, I could be anywhere in the pickup of that satellite. Now, if I pick up 2 satellites, where they intersect is where I could be. And that could be several thousand miles apart. But now, if I use 3 satellites, okay, 3 satellites, it tells me exactly where I am on the Earth's surface, okay? It tells me exactly where I am on the Earth's surface. So I'm going to go through this. I'm going to look at this now. It's going to tell me here, if I'm tracking 3 satellites, that gives me what's called a 2-dimension position on Earth. It gives me my latitude and longitude. Yep. It gives me my latitude and longitude. But this is also a clever system. If I now use 4 satellites, okay, if I can track 4 satellites, it tells me my 3-dimensional position on the Earth. So it gives me my latitude, longitude, and height. above the Earth's surface. Okay, so it gives me latitude, longitude, and height above the Earth's surface. So just remember that now. 3 satellites gives me 2 dimensions in space, or 2 dimensions. 4 satellites, it tells the aircraft its latitude, its longitude, but also its height. I'm going to come back to the number of satellites in a minute. Okay, the next thing we need to look at is the number of satellites. If you look at here, there's 21 satellites. They are in 6 orbits. Okay, they're in 6 orbits. The next thing is called RIAM. Now go look at this, right? Remote autonomous integrating monitoring. Sorry, remote autonomous integrity monitoring. It's an error checker for my satellites, because if one of the satellites is giving out the wrong information, it could put the aircraft somewhere where it's not. Okay, and for RIAM to work correctly, it needs to know, it needs to be able to use 5 satellites. Okay, so my aircraft, my GPS, my aircraft is constantly looking at the information coming from the satellites. And if it has 5 satellites, it can work out, it's got a program, it can work out which one of those is giving it the incorrect information. But as soon as it's only backtracking 4, it can't tell if this one was to go wrong. And if that one goes wrong, we're going to get an incorrect position. So for RIAM, Receiver Autonomous Integrity Monitoring, to continue, if one satellite fails, it needs 6 satellites. Okay, 6 satellites. So what I can say, gentlemen, is 3 satellites gives me 2 dimensions on the Earth's surface, latitude and longitude. 4 satellites equals 3 dimension, latitude, longitude, and height. 5 satellites gives me RIAM. 6 satellites gives me RIAM, but I can actually have, I can basically lose 1 satellite and RIAM will continue. Okay, so 6 satellites is basically RIAM continuous. Okay, it will continue to work when 1 satellite fails. So please remember this: 3, 4, 5, 6. 3 satellites, 2 dimensions on the aircraft surface. 4 satellites, 3 dimensions, longitude, latitude, and height. 5 satellites gives me RIAM, Receiver Autonomous Integrity Monitoring, an error checker. And 6 satellites allows RIAM to continue working when I lose 1 bad satellite. So if you can write that down somewhere and remember 3, 4, 5, 6. Okay, 3, 4, 5, 6. The next thing we're going to look at is something called mask angle. Okay, mask angle. And the definition of mask angle is 7.5 degrees, an angle 7.5 degrees below, sorry, above and below the horizon. So if you look here, there's my horizon. Okay, there's my horizon. And any satellite that's basically below 7.5 degrees above the horizon, we can't use the signal. The signal's either too weak or it's corrupted. Okay, so the aircraft will see the system or see the satellite, but will not use its information because it can't be considered to be correct. Okay, cannot be considered to be correct. So you need to know the definition of a mask angle. It is any satellite that is below 7.5 degrees above the horizon. Okay, below 7.5 degrees above the horizon. Okay, so what do we need to know in GPS? There is 21 active satellites and 3 spare. They're in 6 orbits around the Earth, and they provide information about my position on the Earth. To get a 2-dimension position, I need 3 satellites. For a 3-dimension position, I need 4 satellites. The error checker we call Receiver Autonomous Integrity Monitoring, RAM. Okay, and for that to pick out a bad satellite needs to be picking up 5 satellites, using information from 5 satellites. For RAM to be constantly moving when it detects a bad satellite, it needs 6 satellites to work. And the last thing is, what is mask angle? Mask angle is where we do not use any information from any satellite that is below 7.5 degrees above the horizon. Where am I? Okay, next thing we're going to look at is inertial navigation. This used to be the primary means of navigation for the aircraft. It's now been taken over by GPS. Okay, but all your aircraft will have some sort of inertial navigation system as a backup to GPS, because in certain circumstances the GPS signal might fail. Electrical storms, when you fly very high in the Arctic or the Antarctic, we can lose the signal, or the system might just fail. So we have a backup. It's called inertial navigation. Okay, the inertial navigation system. Okay, or the inertial reference system. It gives you a position where you are on the Earth's surface, latitude and longitude. But how does it get it? This is what we're going to look at. Okay. My inertial navigation, the sensors for my inertial navigation are accelerometers. Okay, they are accelerometers. And what they're going to do, I'm going to put my accelerometer through some electronics, and those electronics are called integrators. Okay, so when I put my accelerometer, and we have 2 of them, a minimum of 2, one is actually placed in the north-south axis, and one is put on the east-west, so north-south and east, west. So we have two of them. And what they're going to do is give me some information. So my accelerometers produce a voltage, or it produce a signal. The first bit you can see there, it gives me acceleration. Acceleration doesn't actually tell me really anything. It doesn't tell the aircraft anything apart from the acceleration forces on the aircraft. But as soon as I put the value of acceleration through an integrating circuit once, it produces velocity. So it tells me the speed of my aircraft across the ground. Remember, an airspeed indicator gives me the speed through the air. And my INS, inertial navigation system, if I integrate the acceleration first, gives me speed across the ground. If I integrate it again, it says the latitude, but I'm going to tell you, let's call it a distance. And the same happens with the second accelerometer. So you have to understand that my accelerometers, we have one north and south, one east-west. We integrate it first, we get velocity or speed, and we integrate it again, we get distance. Now it does say their latitude, but for an inertial navigation system to work correctly, I need to know an accurate starting point, okay? And when I mean an accurate starting point, I'm probably looking at like 37 degrees north, 32 minutes. We're looking at then seconds and fractions of a second for latitude. That's how accurate you have to be. So for my inertial navigation system to work correctly, I have to have a very accurate starting point, okay? It requires the system to have a very accurate starting point. So, how does the system work? Okay, we'll just look at the old system. And what would happen is, if you can see here, gents, in the inertial navigation control panel, the pilot would put in his very accurate starting point, latitude and longitude. Okay, and then my inertial navigation, my inertial reference unit has my two accelerometers. But those two accelerometers are on what's called a gyro stabilized platform. We're on a gyro stabilized platform because any movement up and down or left and right will cause an acceleration force, therefore an error. And before we had GPS, the pilots would have to manually update the inertial navigation system by either flying one of the radio beacons we've talked about, okay, or look at the map and fly over an obvious point in the map. But now, as I said, my inertial navigation system is my secondary navigation system. My GPS is my primary navigation system. So in my inertial navigation system, it constantly is being updated by the GPS. So in my inertial navigation system, how is it updated? Is updated by the GPS, the Global Positioning System. So what do I need to know about inertial navigation or inertial reference system? Its sensors are accelerometers. We've got one accelerometer north-south, one accelerometer east-west. What information do I get out of the accelerometer? If I integrate it once, I get speed. If I integrate it twice, I get distance. For it to give me my latitude and longitude, my change of position, it needs to know a very accurate starting point. Okay, and those accelerometers are placed on a gyro stabilized platform. How is my inertial navigation system updated in a modern aircraft? It takes its positional updates from the GPS. So if the GPS was to fail, the inertial navigation would automatically take over with a very accurate starting point. Okay. Any questions on inertial navigation? Okay. Any questions on inertial navigation? Nope. Is anyone get any questions? Yes.
What should we remember in this this inertial navigation system?
Say that again.
What should we remember for the exam point of view for this inertial navigation system?
Okay, so I've just been through it. Okay, you need to understand what the sensors are, the accelerometers, how they're positioned east-west on a gyro-stabilized platform. The acceleration comes out, it goes to an integrating circuit. The acceleration forces, when they go through an integrating circuit, once produce velocity or speed. When I integrate it again, it produces distance. For it to work correctly, I need a very accurate starting point. Okay. Yep. So that is inertial navigation. Okay. That is inertial navigation. Okay, gentlemen, I think we've done enough today. Okay, do you agree? Yes.
In this inertial reference system, it will primarily depend on GPS, right?
Yeah, it gets its constant updates from the GPS system. So it's constantly getting a very accurate position from the GPS all the time. So if the GPS now fails, the inertial navigation system takes over and it has a very, very accurate starting point. So it knows it's working from a very accurate starting point. So
pilot needs to feed the starting point. If the
the GPS is automatically updating the positional information to the inertial navigation system.
And if the GPS fails, then that I am asking.
The INS takes over, and the longer we go flying, the more inaccurate my position will be. That's why the pilot would have to fly over a beacon to get the exact latitude, longitude of that beacon. Or if he's looking at a map and he flies over a lake, okay, which is on the map, or something he can see on the map, he can update it manually from the position on the map. Okay? But as longer I go flying, the more inaccurate my position in inertial navigation would be. Going way back to the old days when we only had inertial navigation, we used to have four crew. We used to have a pilot, a co-pilot, a flight engineer, and a navigator. And he would use these sextant maps to get the latitude and longitude. Okay? But now our primary means of updating is the GPS. Okay? All happy in that? Anyone else with any questions?
And this is starting point means pigeon position.
Say again?
This starting point means same as the pigeon position.
I can't hear what you're saying. It's very garbled.
starting point means the present position.
Yes, the starting point. If you go to look at the runway, okay, you go to the gate. I can't remember if Kathmandu's got one, but you look at the gate, it might have gate 1, 2, or 3, and it'll have the latitude and longitude written on it. Does it? I can't remember if it does in Kathmandu. But the pilot will know, he can actually look on the maps and he can get gate 1, and then literally he can get the accurate starting point of gate 1 at Kathmandu Airport. That's how accurate it has to be. Because if he was in gate 3, he hasn't got a very accurate starting point. It could be 300-400 yards out. If you think about it, between gate 1 and gate 3, you've got to get another aircraft safely in. So that's how accurate it has to be. Okay?
Okay. Thank you.
Anyone else got any questions? Okay, now have a look at the sheet you've been sent out. Okay, if you want, I mean, I know you've got to go. It's nearly 10 o'clock at night. But if you look at the sheet, it's got a whole load of questions, and it also has the answers at the back. Okay.
Okay,
So,
thank you.
Okay, so they will help you. There's over, I think I've got, for this module, I think there's over, there's 112 questions. We haven't done 112 questions yet. I think we've got up to, we've just got to question 44. Oh, we've got a lot more questions to do tomorrow. Okay, you all happy on what we've done today so far?
Yes.
Okay, have a good sleep, or do some questions, or do some have a sleep and do some questions in the morning. Again, if you get any questions, again, ask me first thing in the morning. Okay, we all happy?
Happy.
It's been a pleasure teaching you, and I will see you tomorrow, gentlemen. I'm about to go and dig some more snow.
Okay, see you tomorrow.
Okay,
Take care.
have a good night's sleep,
Bye-bye.
gentlemen. Bye-bye.
Good night.
Bye-bye.
Okay, have a good day.
And you.